This section is about graphs. So we'll learn various things about graphs. But in this video, we will have introduction to the terminology used in graphs. For introducing terminology, I have taken various example graphs. So through these graphs, let us know the terminology. See, a graph is defined as collection of vertices and edges. So yes, every graph, if you see, it is having vertices. These are vertices. The circled one, nodes are vertices, and the links are edges. The links are edges. So graph is defined as G is equals to VE, where V is set of vertices and E is set of edges. Let us start with the first example. Here is the first example. See, this is a directed graph. So if the edges are having direction, so then it is called as directed graph. There is an edge coming out from 1 and connecting to 4. So this is outgoing from 1 and incoming on 4. Outgoing from 4 and incoming on 3. So it is incident from 4 and incident on 3. In a directed graph, if there is an edge connecting the same vertex, then it is called as self loop. This is a self loop. And if there are pair of edges between same two vertices, like it is connecting from 4 to 3 and then there is an edge from 3 to 4, then such edges are called as parallel edges. The next thing, the number of edges connecting upon a vertex that are coming in is called as in degree, the number of edges connected. Like there is an edge coming from here, there is an edge coming from here. So in degree is 2. And if there is an edge going out, the number of edges that are going out are counted as out degree of a vertex. If there are two vertices connected by an edge, then they are called as adjacent vertices. So these are few terms we have learned from there. Now let us come to this graph. This graph is not having self loop and there are no parallel edges. So without self loop and without parallel edges, a graph is called as simple graph. Then next, let us look at this graph. There are no directed edges. These are non-directed edges or undirected edges. So it is called as non-directed or undirected graph, and in short we can also call it as graph. Graph means undirected, digraph means directed graph. Then in an undirected graph or non-directed graph, the number of edges connected to a vertex is called as a degree, just a degree. There is no in degree, out degree. It is just a degree. And if there is an edge from vertex 1 to 2, for example, there is an edge, then it is taken as in both the directions. So it is assumed as it is from 1 to 2 also and 2 to 1 also. But it is not a parallel edge, it's a non-directed edge. So it is counted either way, 1 to 2 as well as 2 to 1. Then coming to this graph. See, here I have a graph of 7 vertices. And there are two pieces of this graph. There are two components. So this is non-connected graph. It's not connected. There are more than one pieces, more than one component, so they are not connected. This is non-connected graph. And if suppose I draw an edge and connect it, then now the graph has become connected. It is connected. But you can see that there are two components connected here. So we also call it as connected components. A graph is having connected components, more than one components which are connected. Then one more thing. In this graph, after having this edge, if I remove 6, vertex 6 along with the edges, then again it will get divided into two components. Same way, if I remove vertex 4 along with these edges, then again graph will get divided into multiple components. So if there are any vertices in a graph whose removal will split the graph into multiple components, such vertices are called as articulation points. This is an articulation point. So 4 is also an articulation point. 4 as well as 6, both are articulation points. Then in that same graph, if I add one more edge, now there are no articulation points. If I remove any vertex, then graph will not split into multiple components. It remains as a single component. So that is biconnected components we say. It means there may be components, but they are strongly connected, biconnected. Now you can see that it was earlier not connected. I have added one edge, so it's connected. One more edge, now it is stronger. It cannot be broken into components by removing one vertex. So it is biconnected components. So we can simply call it as connected graph or biconnected components also. Now next is this one. This is a directed graph. And in this directed graph, from any vertex you can start and you can reach on all other vertices. You can go to 2, or from there you can go to 5, or you can go to 4, then 3. If you start from 4, you can go to 2 also. From there you can reach 5, you can go to 3, and from there you can go to 1. So from every vertex we can reach all other vertices. It means there is a path between every pair of vertices, or from any starting vertex you can reach all other vertices. If directed graph is satisfying this property, then it is called as strongly connected graph. So strongly is the term used for directed graphs. So same way here, from one vertex we can reach all other vertices, so that's how it is connected. So in non-directed graph we just use the term connected, but here we say strongly connected. Suppose this edge was in this direction, then we cannot reach 5, but it is connected graph only. It is connected, but it is not strongly connected because we cannot reach on all vertices. From 1 if I start, I cannot go on 5. So when we have an edge like this, then it is strongly connected graph. The next thing we will learn about path. Path is set of all the vertices in between a pair of vertex. Like from 1 to 5, the path is 1 to 2, then 2 to 5. Now similarly here, path from 1 to 7 is, you can go to 2, then 5, then 7. This is a path. This is a path, right? Or else I can go from 1 to 3, then 3 to 4, 4 to 2, 2 to 5, 5 to 6, then 7. Path can be of with less number of edges also, or more number of edges also. Shorter length path or longest path also possible. So path is set of vertices which are connecting a pair of vertices. The next term is cycle. If there is a path that is starting from some vertex and going around few set of vertices and again reaching back, then it is called as a cycle. Like from 1 to 2, 2 to 5, 5 to 4, then 4 to 3, then 3 to 1. 2, 5, 4, then 2. It's a cycle. And here also we have cycles. This is non-directed, but still we have cycle 1, 2, 4, 3, 1. So cycle is a circular path, or a circuit we can also say, that is starting from one vertex and ending at the same vertex. The next is this graph, directed acyclic graph, DAG. This is a directed graph and there are no cycles in this one. There are no cycles. If you start from any vertex, you cannot reach that same vertex in any way. You select any starting vertex. So that is directed acyclic graph. There is no cycle. And the last thing is, this directed acyclic graph, we can arrange all the vertices linearly in a single line. Those vertices are arranged in a single line such that the edges are going only in forward direction. The edges are not coming back. If you can arrange the vertices such that the edges are going only in forward direction, then it is called as topological ordering of vertices. This is possible only in directed acyclic graph. So that's all. These are various things we were supposed to know about graphs. In coming videos, we'll learn more about graphs. See, graphs are very useful data structure. Many problems, various problems can be represented in the form of a graph. And if we can solve a graph, then we can solve a problem. So problems are converted into graph and solved. If you want to solve any challenge, then you can convert that challenge into form of a graph and find a solution in the graph. Then you find a solution for a problem. So graph is very useful data structure in problem solving. So let us learn more about graphs in coming videos. In this video, we'll look at the representation of graph, the data structures used for representing graph. See, for representing a graph, we have to represent two things. What are the set of vertices and also set of edges. So for representing them, there are more than one methods, that is adjacency matrix, adjacency list and compact list. Let us look all of them one by one. Yeah, here first one is adjacency matrix. I have already taken a matrix. The graph is represented as set of vertices and edges, and the number of vertices which is represented as n are 5, and the number of edges that are represented with the symbol E are 7. So I have to represent all those vertices and edges. For representing in the form of a matrix, I have taken a matrix of size 5 cross 5, 5 by 5. The vertices are starting from 1 onwards, so here also I have taken matrix starting from 1 onwards. But really when you use a program, C++ program, it may be starting from 0. So you can start from 0 and you can label the vertices from 0 onwards. Now let us see how to represent that graph in the form of a matrix. See, for any two vertices I and j, if there is an edge, then we should mark 1 inside the matrix at that same location I and j. Let me show you. It means if there is an edge I to j, then mark in a matrix ij as 1. Otherwise, it should be taken as 0, means there is no edge. So let me show you how to mark this one. Let us start from vertex 1. Vertex 1 is having edges connected to 2, 3 and 4. So from 1, there is an edge to 2, there is an edge to 3 and 4. Remaining are zeros. 0 means there is no edge. Then let us look at second. From 2, there are edges to 1 and 3. So from 2, there are edges to 1 and 3. And these are all 0. Likewise, I will fill up for all. From 3, it is to 1, 2, 4 and 5. 1, 2, 4, 5. Then from 4, it is connecting 1 and 3 and 5. 1, 3 and 5. Then from 5, it is connecting to 3 and 4. So from 5, it is on 3 and 4. So that's it. See, if there is no edge, I have marked it as 0. So even you can mark it as infinity in the absence of edge. And one more thing, diagonals are representing self loop like 1 to 1, 2 to 2. There are no self loop here. So sometimes we put infinity there in self loops. So it depends on your application, depends on your requirement. Either you can put the value as a 0 or you can put the value as infinity or any other marker that you want to show absence of an edge. The next, let us look at adjacency list. For representing a graph in the form of an adjacency list, we'll take an array of linked lists. So I'll take an array of size 5. This is an array of size 5. This is an adjacency list. So actually this is array of linked list. Now for each location is representing a vertex. So for that location, we will have the set of adjacent vertices. For example, if we take 1, if I take vertex 1, from 1 there are vertices connected to it are 2, 3 and 4. So here we will draw a linked list with those nodes representing 2 and 3 and 4. This is null. Now similarly, who are connected to 2, 1 and 3. So I should have the list of nodes showing 1 and 3. And now similarly for 3, the connected vertices are 1, 2, 4 and 5. I will draw them. Now for 4, connected vertices are 1, 3 and 5. So I will draw 1, 3 and 5 here. 1, 3 and 5. Now for 5, 3 and 4, 3 and 4. So this is array of linked lists showing the edges, and this array itself is showing vertices. So this is the representation. Now I have to show you compact list, but before that let us do some analysis of this one. See, in this matrix there are total 5 into 5 elements are there. Some are zeros and some are ones. So unless we check, we can't know whether there is an edge or not. So for accessing edges, we may have to access all the elements. So total number of elements are depending on the number of vertices, that is n square. So it means any algorithm which is accessing a graph in the form of a adjacency matrix has to access those many elements, process those many elements. So the time taken by an algorithm may be dependent on n square. Then if an algorithm is using adjacency list, then what is the memory consumed here? It is the set of vertices, that is set of vertices V, that is n, plus these are set of edges, but each edge is represented 2 times, so 2 into e I can say. So this is 2e. So the time dependent on set of vertices and set of edges. There it is dependent on square of vertices. So the time taken by any algorithm depends on number of vertices and edges, and it depends which data structure is used by an algorithm. It may be n square or it may be v plus e. 2 times of E is also, we can consider it as E, so it is V plus E. So if you check most of the algorithms, they are analyzed based on V plus E, number of vertices and edges. So that's the analysis of the space consumed by this data structure. Now next, one more thing I will show you, that is weighted graph. See here, I have given weights to the edges of a graph. If weights are given, then we want to store those weights also. Means the cost of this edge is 9, the cost of this edge is 6, and the cost of this edge is 8. So we want to store those weights also. So how to store that? So in the form of an adjacency matrix, instead of marking this as 1, this edge as 1, we can mark it with a weight, that is 9. So edge from 1 to 2 is 9, and the cost of edge from 1 to 3 is 4. Cost of an edge from 1 to 4 is 6. So in this way, all these ones can be changed in the form of a weights of those edges. I'll change them. So here I have changed all of them. Now we can call this as cost adjacency matrix. Instead of just calling it as adjacency matrix, we call it as cost adjacency matrix, because the matrix is representing the cost of edges. Then how to represent those weights in a adjacency list? See here, for the vertex 1, I must have all these vertices which are adjacent. Then along with this, inside the node itself, I should also have a weight stored here. 1 to 3 is 4 and 1 to 4 is 6. Likewise, you can fill up all these. So along with the vertex number, the weight of an edge is also stored inside the list itself. So now it will be called as cost adjacency list. So that's all about these two representations. Now next, let us look at compact list representation. In compact list representation, we will have a single dimension array for representing a graph. What should be the size of that single dimension array? See, the vertices are 5. We should have number of vertices, plus as each edge is represented in two way, that is 1 to 2 and 2 to 1. So 2 times of edges, and I should also have one extra space. So how much it is? 5 plus 2 into 7 plus 1. This will be 20. Then one more thing. I am starting indices from 1 onwards. I am not using index 0. So for that I need one more extra space, that is 20 plus 1, 21. So here I will draw an array of size 21. So here I have an array of size 21, indices starting from 0 up to 20. So total 21 spaces. Then how to represent this? See, this first 5 locations are representing vertices. There are total 5 vertices. So first 5 spaces. I am not using this index 0. So from 1 to 5 they are representing vertices. Total 5 vertices are there. Then for each vertex I should have adjacency list, means who are adjacent to it. Like for vertex 1, adjacent vertices are 2, 3 and 4. But now I will not be using weights, I will remove these weights. So for 1, adjacent vertices are 2, 3 and 4. So this I have to write down. So where to write down this? See here, leaving this location vacant. I will not use that location. I will show you why I am leaving it vacant. So from here, 2, 3 and 4. These are the adjacent vertices of vertex 1. See, the adjacent vertices of vertex 1 are 2, 3 and 4. They are starting from index 7 and ending at 9. So I will write down that 7 here, just 7 here. This means that the adjacent vertices of vertex 1 are starting from index 7, that are 2, 3, 4. Then where they are ending? They are ending at 9. So I did not mention that. I have just mentioned the starting point. Now let us take other vertices. For vertex 2, the adjacent vertices are 1 and 3. So I'll mark them 1 and 3. So these are from 10 to 11 only, just 2 places. So that is starting from 10. So that 10, index 10, I will write here. This means that the adjacent vertices of vertex 2 are starting from index 10 onwards. So 10 and 11, they are ending at 11. Now, as we have there 7 and 10, now observe this. The adjacent vertices of 1 are starting from 7 onwards. Okay, 7, 8, 9, stop. Why? Because the next location belongs to 2. So 7 and 10 together gives the starting and ending point for vertex 1. So that's how just we keep the starting index of adjacency list of vertices. Next, let us write down rest of those. That is for 3, the adjacent vertices are 1, 2, 4, 5. 1, 2, 4, 5. Starting index is 12 and this belongs to vertex 3. This belongs to 2. Then for 4, 1, 3, 5. So 1, 3, 5. These are for 4 and the starting point of this one is 16. Then for 5, adjacent vertices are 3 and 4. So these are 3 and 4 and the starting point is 19. This is starting point 19 and this belongs to 5. I have filled all of them. Now, from 7 to 10 minus 1, list of vertices 1. From 10 to 12 minus 1, 11. List of vertices for vertex 2, these two. Then for 4, 16 to 18, yes, 16 to 18. Then for 5, 19 to what? 19 to what? 19 to 20, means 21 minus 1. So here I should write down 21. So it gives the ending point for this vertex list of 5. That's why we have kept this place blank so that we can store the index that is outside the size of an array, that is 21. 19 to 20 minus 1, 20. So that's it. This is the compact list representation. I have not stored weights. If you want to store weights, then you should have one more array. It means two-dimensional array, 2 rows and 21 columns. And each location you can have the vertex number. Below that you can also have its weight. Then what is the space consumed by this one? This is number of vertices and number of edges 2 times, so plus 2e. See, this we call it as n and this is 2e. If we say e is also equal to n, this is 2n. So total it is 3n. It is order of n. So it's linear. If we assume that n and e are equal, if we assume they are not equal, but we assume. So why we are assuming is n is a linear value, e is also linear value. It's not e square, right? E square means quadratic. It is not n square. N square means quadratic. So this is also linear, this is also linear. So both are linear. So n means this is not variable n. This means linear. So the space consumed by compact list is linear. That's all. So in the coming videos we will see algorithms on graphs. Let us look at the representation of a directed graph. Already we have seen it for non-directed graph. We follow the same method, that is adjacency matrix and adjacency list. So here I have a directed graph. Let us see how to represent that one using adjacency matrix. I have taken a matrix of size 4 by 4 because here the number of vertices are 4. Number of vertices are 4 and the number of edges are 5. 4 vertices and 5 edges. Depending on the number of vertices, we should take a square matrix of size 4 by 4, that is n cross n. Now each row or column represents a vertex, like first row represents first vertex or first column also represents first vertex. Now just like for a non-directed graph, here also we have to mark value 1 wherever there is an edge. So let us quickly do that. 1 to 2 and 1 to 4, there are edges 1 to 2 and 1 to 4. Remaining are zeros. Then 2 to 3, there is only one edge, and 2 to 1, 2 to 2, 2 to 4, there are no edges. 3 to 1, there is an edge. 3 to 1, there is an edge, and remaining all are zeros. 4 to 3, there is an edge. Remaining are all zeros. That's all. This is the representation for a directed graph. In non-directed graph, when there is an edge from 1 to 2, we were counting it either way, 1 to 2 as well as 2 to 1. But here, as it is having direction, just we will take it as 1 to 2. Now next, let us look at adjacency list representation. For adjacency list, here is an array of linked lists that already we have seen in non-directed graph. Each location in an array is representing a vertex there. Then whoever are the adjacent vertices, we should have the adjacency list. So for 1, who are adjacent, 2 and 4. So these are the list of vertices who are adjacent. So this is adjacency list. Then for 2, there is only one vertex, that is 3. And for 3, there is only one vertex, that is 1. And for 4, there is only one vertex, that is 3. That's all. This is adjacency list. Then one more thing to observe here. See, I want to know what are the edges going out from vertex 1. From vertex 1, the edges going out are 1 to 2 and 1 to 4. Yes, 1 to 2 and 1 to 4. Then I want to know what are the edges that are coming in on vertex 4. So check the column. Yes, there is an edge coming in from 3 to 1. 3 to 1. Check the column. So 3 to 1, there is one edge coming from 3 to 1. So it's coming in. So I can know in degree of vertex 1 by taking column, out degree of vertex 1 by taking number of ones in a row. Like there are 2 ones, so out degree is 2. But in adjacency list, we only have out degree. But for in degree of vertex 1, I should search all linked lists and find out wherever 1 is occurring. So I found 1 one time. So in degree is 1. I want to know in degree of 3. 3, yes, 1 time, then 2 time. So in degree of 3 is 2. So I have to check all linked list. But for out degree of vertex 1, just count the number of nodes in its own linked list. For this, 2 nodes are there. So the length of the linked list is 2. So out degree is 2. In degree we cannot know. Suppose knowing in degree is also important for us, then we can have one more type of adjacency list, that is called as inverse adjacency list. So I'll draw it here. So for inverse adjacency list, the method is same. We will take array of linked list. Then whatever the edges that are coming on vertex 1, we will draw them here. So the edge is coming from 3, and on 2 the edges are coming from 1, and upon 3 the edges are coming from 2 and 4. See, for 3 there are 2 and 4. So you can see that there are 2 edges coming in. Then for 4, there is an edge coming in from vertex 1. So this is inverse adjacency list. So this is showing going out edges, and these are edges that are coming in. So if that is the requirement of an application, then you can have inverse of adjacency list also, and also you can have actual adjacency list. So that's all about representation of directed graph. You can also prepare a compact list, but you can show outgoing edges, or else separate. You can have inverse compact list also, that you can do it by yourself. So already we have seen compact list on non-directed graph. It will be in a similar fashion. Then little bit of analysis. If a directed graph is represented in the form of a adjacency matrix, then total number of elements are n into n, that is n square. Any algorithm which is processing upon this data structure may have to go through all the elements of this matrix, at least to check whether there is 0 or 1. So it has to process all the elements. So the time taken may be n square if it is processing all the elements once. So the minimum time we can say, that is n square if adjacency matrix is used. And if any algorithm is using adjacency list, then the time taken for processing all this is number of vertices, n, that is v, and these are all edges. So e, that is small e. So this we can say both are n. For assumption, we can assume both are n, and we can say order of n, and this is order of n square. So if adjacency list data structure is used, then the time may be less, and if matrix is used, then the time may be more. So whenever we analyze any algorithms, we will analyze their time assuming that they are using adjacency list. So we assume that the time taken for accessing the data structure may be n. Actually, the graphs are analyzed based on set of vertices and set of edges. How much processing is done is represented in the set terms of vertices and edges, because there are two different lists, list of vertices and list of edges. So that's all with the analysis. In coming videos, we will see algorithms on graphs. Here we look at breadth first search traversal of a graph. As a graph is a nonlinear data structure, there are two suggested traversal methods like breadth first search and depth first search. These are similar to tree traversal methods. How they are similar to tree traversal methods, I'll show you. Let us start with breadth first search. See, the breadth first search is similar to level order of a binary tree. But here we may not get a binary tree, just we get a tree. So whatever it is, breadth first search is same as level order. How it is same as level order? Let us understand this. I have an example graph taken here. This graph, I can convert it in the form of a tree. How? See, a graph without any cycle or without any closed edges is a tree. So let us prepare a tree for that graph. So I'll show you here. The vertices are 1 to 7. So I'll start from vertex 1. This is vertex 1. Now to a vertex 1, the connected vertices are 2, 3 and 4. So I'll take all. So first is 2, then second is 3, then 4. So for vertex 1, 2, 3, 4 are completed. Now let us see who are adjacent to 2. Who is adjacent? Only 3. So actually I am preparing a tree. So this edge, if I include, it will form a graph because it will form a cycle. So what I'll do is I'll put a dotted edge, just a dotted edge. So I have completed these 3 edges plus this one. Now next we have 3 also. So who is adjacent to 3? So from 3 I can go on 5 as well as on 4. So a new vertex is 5. I can go on 4 also. So I'll draw a dotted edge because 4 is already there. Then next from 4 where I can go? 1 that is already over, 3 already over, then 5. So 5 already is there. So I will draw dotted edge. The next is 5. From 5 I can go on 6 and 7. So I will draw here 6 and 7. That's all. I have converted a graph into a tree. I should not say binary tree because this node is having 3 children. So it's not a binary tree, just a tree. Now in this tree, if you observe, I have all 7 vertices. Then if I count the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have all the 9 edges and I have dotted those edges which are trying to form a cycle. Now if you hide those dotted edges, it's a tree. So I have formed a tree for the graph. Now take the level order. First vertex is 1, then next level is 2, 3, 4. So 2, 3, 4. The next level is 5. Okay, 5. Next level is 6 and 7. 6 and 7. That's all. This is breadth first search. Then this is the result. Is this is the only result possible? No. When you perform breadth first search, you can get a different results, and whichever result you want, you can take that one. So how different results are possible? Let us see. I will again draw a tree for this one. So I'll again draw from vertex 1. Now who are adjacent? Adjacent to 1 are 2, 3 and 4. Do I have to take them in same order? No, you can take them in any order. So I will change the order now. So first I will take 4, then 2, then 3. So the objective here is you must visit all adjacent vertices of vertex 1. Vertex 1 is the starting vertex. So I have visited all of them. In which order, it doesn't make any difference. So first time it was 2, 3, 4. Now it is 4, 2 and 3. So yes, this order is also correct. Then whose adjacent vertices I should take next? 4s. Who are adjacent to 4? 3 and 5. 3 is already there in the tree. So 5 I should take. So next is 5. And for 3, I'll draw a dotted edge. The next whose adjacent I should take? 2. So for 2, who is adjacent? Just 3. So I will draw a dotted edge. Then next is 3. Who is adjacent to 3? 4, which is already there, and 5 is already there. I'll draw a dotted edge. Then next for 5, who are adjacent? 6 and 7. So do I have to take them in the same order, 6 and 7, or you can change the order? You can change the order. So I will take first 7, then 6. Then from 7 and 6 there are no other edges. That's all. Then what is the level order of this one? So breadth first search is first 1, then 4, 2, 3, 4, 2, 3, then 5, 5, then 7, 6. This is the breadth first search. So this breadth first search is also correct. So yes, for a graph, there can be various breadth first search possible. Like if you see here, instead of 4, 2, 3, I could have taken 4, 3, 2 also. Yes, I'll get a different result then. This is over. Next. Who is the starting vertex in both these trees? 1. Is it necessary that you start from vertex 1 only? No. You can start from any vertex you like. Shall I start from vertex 4? Yes, you can start from 4. So I will draw it. 4 is the starting vertex. Who are adjacent to 4? 1, 3 and 5. In which order I can take? I can take them in any order. So first I will take 5, then 1, then 3. Then whose adjacent I should take? 5. For 5, 3 and 6 and 7 are adjacent. So 3 is already there. So 6 and 7. So I will take first 7, then 6. Okay, no problem. I can take it. Then whose adjacent I should take? 1. So for 1, who is adjacent? 2 and 3. So for 1, 2, I will draw it. 3, it's already adjacent. Then for next 3, who is adjacent for 3? 2, 5 and 4. So 4 is coming from 2, I should draw an edge, right? 5 already there is an edge. That's all. Next, I should go to adjacent vertices of 7 and 6. So there are no adjacent vertices of 7 and 6. I got this result. The tree is different. Starting vertex is 4. So what is the breadth first search for this one? Let us take a level order of this one. First is 4, then 5, 1, 3, then 7, 6, 2. This is the level order. So these are the 3 examples I have shown you. Now let us summarize and understand what is breadth first search. Now listen carefully. Breadth first search says that you can start traversal from any starting vertex you want. It should not be or need not be vertex 1 only. You can start from any vertex. That's the first point. So I have started from 1 also, 4 also. I can start from 3 also. Then second thing, when you have visited a vertex, you should explore that vertex completely. What does it mean by exploration? See, when we have selected 4, then we have visited all adjacent vertices. So visiting all adjacent vertices is exploration. So whenever you select any vertex, explore all its adjacent vertices. Then select the next vertex and explore all its adjacent vertices. Then, while exploring, what should be the order of visiting the vertices? You can visit them in any order. Like for any vertex, there are more than one neighboring vertices. You can visit them in any order. So this is the idea about breadth first search. Now let us learn breadth first search freshly as it is found in the textbooks and everywhere. How it is defined, the same way I will define and explain you. See, breadth first search can be defined by using 2 terms. First term is visiting. Visiting a vertex means going upon a particular vertex. That's the first point. And the second thing we should understand is exploring. Exploring means exploration of a vertex. If I say, if I am on vertex 4, exploring vertex 4 means visiting all the adjacent vertices of 4, like 1, 3 and 5. Visiting all adjacent vertices of vertex 4. So exploration means visiting neighbors, and visiting means just going on that vertex. So these are the 2 terms I'll be using for explaining breadth first search. So let us start performing breadth first search upon this graph. First thing, from which vertex you want to start? You can start from any vertex. I will start from vertex 1. Vertex 1. So vertex 1 is visited. So here I will write down visited vertices. This is 1. And this visited vertices, in which order they are visited, that gives me breadth first search. Then I need one more thing. I need queue data structure. So I will take a queue. And I will drop that 1 in the queue. This is the initial point. Select the starting vertex, visit it, and also drop it in the queue. Now whatever I am showing you is repeating. This was the initial one. Now the steps are repeating. Look at this. Take out a vertex from queue. Okay, take out a vertex and explore that one. So start exploring 1. Who are adjacent to 1, 2, 3 and 4? In which order I can visit? You can visit them in any order. So I will first go on 2. 2 is visited. Insert it in queue. The next is 3. 3 is visited and insert in a queue. The next is 4. 4 is visited, then insert it in a queue. Now, one is completely explored. So once you select a vertex for exploration, explore it completely. This we have done. Now again repeat, select a next vertex for exploration. From where? From Q. So in a Q, next vertex is 2. Start exploring 2. So from 2, what are the vertices that I can visit? Only 3, which is already visited. So just draw a dotted line. So 2 is completely explored. So next, select a vertex from Q and start exploring it. 3. From 3, what are the vertices that I can visit? I should explore 3. So 2, 4 and 5. So 2 is already done. 4 and next is 5. I'll draw it like this. So 5 is a new vertex visited and inserted in a Q. Now 3 is completely explored. Select the next vertex for exploration. 4. Who are adjacent to 4? 5 and 3 that are already visited. So just 5 dotted line. Now 4, there are no new vertices from 4. So 4 is completely explored. Now next vertex from the Q. 5. Who are adjacent to 5? 6. Visit 6. Add to the Q. 7. Visit 7, add it to the queue. Now 5 is completely explored. Next vertex for exploration, 6. Nobody is adjacent to 6. So 6 is completely explored. We don't say it cannot be explored. We say it is completely explored. Next vertex from Q, 7. 7. There is nothing adjacent to 7. So 7 is also completely explored. Q became empty. Breadth first search ends. And the result of breadth first search is 1, 2, 3, 4, 5, 6, 7. This is one of the result. As I said that when I am exploring vertex 1, 2, 3, 4, even I can change the order. So if you change the order, you get different breadth first search. And it is valid. So for a given graph, there can be various breadth first search. Importance is not the order in which you are visiting. Importance is that you are visiting all the vertices. That is more important. So that's all. I have given you one example and already I have shown you how the various examples are possible. Then learn few things from this one. This tree is called as breadth first search spanning tree. It is a breadth first search spanning tree. And these dotted edges what I am drawing, these can be called as cross edges. These cross edges in a breadth first search tree will be connecting from one vertex to a vertex in the next level only, not far away vertices. You will not find edges connecting from 2 to 6. No. If there is any cross edge in a breadth first search spanning tree, it will be connecting two vertices with the adjacent levels. That is one level to very next level only. So that's all about spanning tree. Now the next thing, how much time it has taken? Let us do analysis. See the time taken for performing breadth first search. So what is the work we are doing? Analytically we are looking at, right? Analytically. The work we are doing is we are visiting all the vertices once. So how many vertices are there? N vertices are there. So the time is order of n. That's it. Then how about inserting and deleting in a queue, and also we are checking whether a vertex is visited or not. More than one vertices are processed here. We ignore them. Analytically we ignore them. We say the time is order of n. So analytical time for breadth first search is order of n. That's all. Next I will show you few valid breadth first search without drawing any tree and all. Just I will write down few breadth first search so that you can understand all these are correct. First one, I'll start from vertex 1. Okay, vertex 1. Then explore vertex 1. 2, 3, 4. No, I will take 4, 3, 2. First 4, then 3, then 2. 1 is completely explored. I should explore 4 now. From 4, 3 is already done, 5. Okay, next is 5. So 4 is completely explored. Now start exploring 3. From 3 to 5, which are already there, then 3 is completely explored. Explore 2. There is nothing nearer to 2. So explored. Then from 5, 6 and 7. 6 and 7. No, I will visit first 7, then 6. Okay, no problem. You can take first 7, then 6. 5 is explored. Now explore 7. There is nothing adjacent to 7, so 7 is explored. There's nothing adjacent to 6, so 6 is also explored. There's one answer. Then, second one, I'll start exploring from vertex 5. Okay, start from 5. Visited. Explore 5. Who are adjacent? 3, 4, 6, and 7. So I will take 7, 3, then 6, 4. Okay, 6, 4. Then 5 is completely explored. Explore 7. There is nothing adjacent to 7. Then explore 3. For 3, adjacent vertices 2 and 1. So 2 and 1. Now actually I have finished with all the vertices. I can stop now instead of continuing because total 7 vertices are there. All 7 vertices I got. So I can stop it here. As I am doing it manually, I can stop it. Otherwise, for every vertex, it should be checked. Next, third one. I'll start from vertex 2. From vertex 2, first visit vertex 2. Start exploring 2. Adjacent vertices are 1 and 3. I'll take 3 first, then 1. Okay, valid. 2 is explored. Now start exploring next. Which one? 3. From 3, 4 and 5. So I will take first 5, then 4. Okay, 5, then 4. No problem. 3 is explored. Now start exploring 1. From 1, 2 and 4 they are already visited. So 2 and 4 visited. So 1 is already explored. Then 5. Who are adjacent to 5? 6 and 7. I'll take 7 and 6. Okay. So 5 is explored. Now start exploring 4. There is nothing adjacent. Already they are visited. Then for 7, nothing adjacent. 6, nothing adjacent. So I got this answer. So 1, 4, 3, 2, 5, 7, 6 is correct breadth first search. 5, 7, 3, 6, 4, 2, 1 is also correct. Even 2, 3, 1, 5, 4, 7, 6 is also correct. The differences are the starting vertex is different sometimes and the order in which the vertices are explored or visited, that is also changing. So all these are valid breadth first search for this graph. So that's all about breadth first search. Next video we'll look at an algorithm for breadth first search. Now let us look at an algorithm or a program for performing breadth first search. The same graph which I have already explained you, for that I have a adjacency matrix. 7 vertices, so the order of a matrix is 8 by 8. This is a two-dimensional array of size 8 by 8 because the vertex number is starting from 1 onwards, so I am not using index zeros. I left them blank, so whatever the value is there in them, I don't bother because I'm not using from there. I'm using from 1, 1 onwards. So already I have marked this adjacency matrix wherever there is an edge, I have marked it as 1 and the remaining are zeros. Now for performing breadth first search, I should know which vertices are already visited and which are yet to be visited. So for that I have taken an array that is called as visited. Then also we need one data structure for queue, that is where we insert and delete or NQ and DQ vertices. So also I have a queue. Now let us write on a function. So for function, first of all, this visited array should be initialized to 0. Means none of these vertices are visited. Now breadth first search. Assume that for this algorithm or this function, all these are global. If you think that no, we should pass it as parameter or declare them locally, you can declare, you can pass them as parameter. So while giving a demo, we will decide that time. But right now, function just takes integer I. What is this? This is starting vertex, whatever the starting vertex is. So I can call this function by passing 1 or 4 or 5, anything as a starting vertex. So this is the starting vertex. So if you remember the procedure, the first thing that we did is we have visited that first starting vertex, this vertex. So I will first of all printf percentile d I. So whatever the starting number, suppose it is 1, then 1 is printed. So the output, that is breadth first search result, I will print it on the screen. So this is first vertex. Then I should mark this vertex 1 as visited. Whichever the vertex is given, I should mark it as visited. So I'm assuming it is 1, right? Let us say this is 1. Then here, visited of 1, I should mark it as 1. So visited of I, mark it as 1. So this is mark it as 1. So this is already visited. Then I should NQ this vertex in that queue data structure. So NQ in a queue vertex I. See, NQ, DQ and the array for the queue that we already have learned, we are using data structure, so we should have the complete implementation with us. This may be a array representation or it may be a linked list representation. How the queue is implemented, we don't bother. So we can borrow the code of queue here. So I'm directly calling function NQ. So this vertex 1 is inserted. Now the repeating procedure starts, loop starts. So I'll write a loop. Condition, I will write it afterwards. So I'll write the condition afterwards. Now inside the loop, what we have to do? Take out a vertex from the queue. So you assign DQ from queue. So I am taking a vertex that is deleted from the queue in a variable u. So I will declare a variable u here. So u is the vertex number that I am going to explore. I have to explore. So what is that number? 1. So this is u. I am calling it as u. Now when I am exploring vertex 1, then I should visit all adjacent vertices. Who are adjacent here? See, this is 0, 1, 1, 1. So who are adjacent? 2, 3 and 4 are adjacent. Remaining 5, 6, 7, they are not adjacent. So I should visit all adjacent vertices. So it means if it is marked as 1, it is adjacent. So for scanning through this whole row, I should have a for loop. So for that, I will take a for loop. For v assign starting index 1 onwards, 1, v is less than or equal to n. N is the number of vertices and assume it is global. N is global. Then v plus plus. This loop will take me through all these. So I am calling these vertices as v. So this is v, right? V is 0, v is 1. So wherever it is marked as 1, I should take it as a vertex, visit it and insert it in a queue. So while visiting this, I should check if, let us say matrix name is A. So if A of U and V is equal to 1, means there is a edge. This is adjacent. And also one more thing, it should not be visited. Like 2 is not visited, right? If it is not visited, then I should visit it. And visited of V is equal to 0, means it's not yet visited. If there is an edge and it is not visited, then I should do two things. Visit that vertex. So for visiting, I should first printf %d vertex v, and I should mark that vertex as visited. So visited of v as 1. Visited of v as 1. And also I should insert that vertex here. NQ that vertex v. So these are all the things I should do inside if. This process should continue for this for loop and also while loop. So that's all. This is the repeating procedure. See, I have written 3 statements in a single line. Print it, mark it visited, and drop it in the queue so that it should be explored next. So then this loop will visit all the adjacent vertices. So who are adjacent? 2, 3, 4. So 3 will also be marked here and 3 is inserted. 4 is marked as visited and 4 is visited. So every vertex is printed, marked visited and inserted. Then loop ends, then come back to while loop. This while loop should again take out a vertex from the queue and start exploring it. So the next vertex will be 2. So this process will continue. How long this loop should work? As long as queue is not empty. Not is empty queue. So this is exploring all the vertices and this is visiting new vertices. That's all. This is the program for breadth first search. So I'll give a demo for this one. When I write down the code, the same thing I may be writing it. Or if any changes required, I will do that. Now one last thing in this one is how much time it has taken. Loop, inside that loop. How many times? N vertices, N time. What about outer loop? As long as queue is empty. How many vertices will come in a queue? Almost all. So how many vertices? N. So this is N, this is also N. So the time is how much? N square, order of n square. But if you remember in the previous video, I said that the time taken for breadth first search is order of n because we are visiting n vertices. Yes, that was analytical time. But really, when we write the program, we realize that we have to scan through this matrix, all the elements, and it's taking extra time. Then one more point. I already told you when I have discussed about adjacency matrix that if any algorithm is using adjacency matrix, then the time is dependent on n square. So yes, it is taking n square. So if you imagine this program will scan almost all the elements in the matrix row by row. Yes, depending on whichever vertex is being explored, it will scan all the elements in a row. So the total time is n square. So this is implementation wise, the time is n square because the data structure we are using is matrix. If you are not using matrix, if you are using adjacency list, then the time may be different and it may be order of n because the time will be dependent on number of vertices and number of edges. So we can say it is order of n. So then the implementation using linked representation, I will directly give you a demo. That's all in this video. Now in this video, we'll look at depth first search. This is one of the graph traversal method. This is similar to pre-ordered traversal of binary trees or trees. Let us understand how it works. So for understanding, we should know two terms. First is visited. Whenever vertex is visited, when we have reach, we call it as visited. Second thing is exploring a vertex. Exploring a vertex means visiting all adjacent vertices. Like suppose one adjacent vertices are 2, 3 and 4, visiting all of them. So based on these two things, I will define and explain depth first search. So let us perform depth first search upon this graph. Here I will be writing the result of depth first search and it uses a stack, so I will use a stack also here. Now let us start. What should be the initial starting vertex? You can select any vertex as a starting vertex. So I'll select starting vertex as 1. Okay, 1 is visited. 1. Once it is visited, start exploring vertex 1. So who are adjacent to 1? 2, 3 and 4. Which one I should go? I can go on any starting vertex. So I can go on 4 also, 3 also, 2 also. I will go on 2. Okay, 2. 2 is visited. 2 is visited. Then, what is the next vertex of 1? Adjacent vertex is 3. No, don't go on next vertex of 1. Suspend 1, exploration of 1 and start exploring 2. Then what to do with 1? Push it into the stack so that we can continue its exploration afterwards. Now we are on vertex 2. Start exploring 2. From 2 we can go on 3. Okay, go on 3. 3. Suspend exploration of 2 and start exploring 3. So 2 in the stack. So it means whenever we get a new vertex, we will suspend the old or current vertex and we will start exploring a new vertex. Yes, that is the approach of depth first search. Explore 3. From 3 where I can visit 4 as well as 5. I prefer going on 5. Okay, go on 5. Then what about 3? Push it into the stack. Suspend its exploration. We have visited 5. Then from 5 where I can go? I can go on 6 and 7. So first I will go on 7. 7 is visited. Push 5 into the stack so that we can explore it afterwards. Start exploring 7. From 7 I cannot go anywhere. Then 7 is completely explored. If you have visited all adjacent or there is no adjacent, we say it is completely explored. Then go back and continue the exploration of previous vertex. Where it is? In the stack. Pop out. We are on 5 now. Start exploring 5. Next vertex is 6. Okay, visit 6. Push 5 again into the stack and start exploring 6. From 6 we cannot go anywhere. So this is completely explored. Go back to the previous vertex. Pop out 5. So we are again here. From 5 I can go on 4 also. Yes, go to 4. Push 5 again into the stack and start exploring 4. From 4 where I can go? From 4 I can go on 3 and 1. 3, it's already visited. 1, which is already visited. So this is the first time I came across already visited vertices, so I have drawn a dotted edge there. Now 4 is completely explored. Go back to previous vertex 5. Continue its exploration. From 5, we can go on 7, 6, 4 or 4, 6, 7. All of them we have visited. So 5 is completely explored. Go back on a previous vertex and continue its exploration. Who is that? 3. From 3. So who are adjacent to 3? 2, 4, 5 as well as 1. So 2 from there only we are coming. 5 we have already visited. 4 is already visited. Dotted edge is also there. But 3 to 1 there is no dotted edge. So I will draw a dotted edge here. 3 is completely explored. Take out next vertex. 2. 2 is completely explored. Take out next vertex. 1 is explored. So by the time when you return and go back to the previous vertices, we will find them they are already explored. So once again, I'll explain depth first search. You can start from any vertex you like. Then you have to explore it. And once you got a new vertex, suspend its exploration, start exploring new vertex. This is how we define. So we have seen this result. The tree that we got is depth first search spanning tree. This is depth first search spanning tree. And in this, the dotted edges that we are getting, we call them as back edges. And if you remember, when I was on 4, I have drawn this edge. When I was on 4, I have drawn this edge. From 3, I have drawn this edge. So these are back edges connecting back to the already visited vertices. So they are called as back edges. So this is one of the depth first search. We can have various depth first search traversals for the same graph. Then next thing, I said that depth first search is just like pre-order of a tree. So, but this is the tree, right? This is the tree. It is a depth-wise generated, not level-wise, depth-wise generated. Perform pre-order on this one. So like, but just by moving a finger, we can get it. 1, 2, 3, 5, 7, then 6 and 4. 1, 2, 3, 5, 7, 6, 4. So for this tree, it is pre-order traversal like. The next thing, we will see the analysis. What is the time taken by this depth first search method? So the time depends on the work that we are doing. What we are doing here, we are visiting all the vertices once. So how many vertices are there? N vertices are there. So the time is order of n. So the time taken for depth first search traversal and this analytical time. Remember this, when we write the program may be taking more time because it depends on the data structure that we are using. If you are using adjacency matrix, then it may be n square. If you are using adjacency list, then it may be n. So analytically we say the time taken is order of n because we are doing nothing, just we are visiting all the vertices once. So that's it. I have explained you depth first search. Now I will remove this and show you various valid depth first searches. So you get the idea how we can perform depth first search in various ways. Now let's perform. I'll write down the results just nearby this graph. First one I am writing, starting vertex. We can select any vertex as starting vertex. So I will select vertex 1. Then from there where I want to visit, I can visit anywhere. So I'll go on 3. Then from 3 I will go on 5. Okay. Then from 5 I will go on 4. Then from 4 I cannot go further because already 1 is visited. Come back to 4. From 4 there is no other route. Come back to 5. From 5 I can go on 7. Okay, 7. From 5 I can go on 6. Yes, 6. Then come back to 5. Right? This cannot be explored further. So this is completely explored. Go back to 3. From 3 I can go on 2. This is also valid. Second one. Starting vertex is 1. 1 to 2. Okay. 2 to 3. Okay. From 3 I can go on 4. From 4 I can go on 5. From 5 I can go on 6. From 6 I cannot go anywhere. Go back to 5. Come on 7. That's also valid. Then one more. Third one. I'll start from vertex 1. Okay, 1. Then I'll go on 4. Yes. From 4 I will go on 5. From 5 I will go on 7. From 7 I cannot go further. Come back to 5. Then from 5 go to 3. Okay, 3. From 3 go to 2. 2. From 2 this is already visited. Go back. From 3 I cannot go anywhere. Go back. See, 2 back, 3, then 7 already gone. 5, I'm on 5. From 5 I can go on 6. Yes, 6. From 6 I cannot go anywhere. Go back to 5, go back to 4, go back to 1. So how to go back? That stack will help you. Or else you practice this, you can get it easily. It's not difficult. Just you do paperwork by yourself. Do it once. Then one more I'll show you. I want to select some other vertex as starting vertex. Okay, select it. Which one? 4. From 4 I can go to 1. From 1 I will go to 3. 2 I skipped. I came on 3. Yes, I can go anywhere. From 3 I will go to 5. Okay, from 5 I will go to 6. Go back to 5. Go to 7. Then this is finished. Then go back to 3. From 3, 2 is remaining. Take 2. This is also valid. So these are various possible depth first search with a different starting vertices or different order of visiting, and all these are valid. Usually students believe that there is only one method, one answer we get. No, you can get different answer. See again, the answer that you are getting is not important. Visiting all the vertices is very important. You should visit all the vertices. So that's all about depth first search method. We will see a program or algorithm on this one. In this video, we'll look at a program or algorithm for depth first search. As we have already seen that a depth first search uses a stack. So if we write a recursive function, it automatically uses a stack. So for writing depth first search, already I have taken a data structure for this graph. This graph is represented as an adjacency matrix. See, there are 7 vertices, so I have taken 8 indices, so 8 by 8, 2-dimensional array. But this 0th row and 0th column I am not using it. And then this is a visited array. All are zeros, means no vertex is visited. Then what is the procedure? This is depth first search. Suppose a vertex u is passed, means the starting vertex. Starting vertex can be anything, let us say 1. If the starting vertex is 1, then what I have to do? First of all, check whether that vertex is visited or not. If visited of that vertex is equal to 0, means it is not visited, then visit it. So before visiting, print that vertex. Print %d vertex u. Print this one. This is printed. Then mark it as visited. See, assume that this is 1. Mark it as visited. Visited of u is 1. So mark this as 1. This is visited. Then start exploring it recursively. So for that I need a for loop. So for v assign 1, v is less than or equal to n is the number of vertices, v plus plus. Then this for loop will go through all these elements in this first row, and every element we should check whether it is 0 or 1. If it is 1, then it's an edge. So here I will write down, if it is an edge in a vertex in a 2D array, that is matrix, at location u comma v, if it is equal to 1 means there is an edge, like u to v. Let us say v is a 2, so there is an edge. So perform depth first search on 2. So perform depth first search on 2. That is v. That's all. End of if, end of this one. So this will call itself again on vertex 2. Now this will be 2. And 2 is not visited, not visited. Print 2. and mark it as visited. Mark it as visited. Then scan through all the adjacent vertices of vertex 2. So now this is U. This is U because U is 2 now. So it will scan through this one. First one V, it's already visited. So nothing will happen. Next 0, it's not 1. So it will not call upon this. Then upon 3 it will call. So it will call upon 3 again. So this how it will continue. To avoid the call, if it is already visited, I can add one more condition that and visited of V is not equal to 0. Then only call. If it is already visited, it will not call the function. Anyway, if it calls also, this condition will stop it. Then how stack is used and all, I will show you. Then how recursion work, you know very well. You can trace this and check upon any small graph. This is a sufficient small graph. It's not too large or too small. So upon this graph, you can try this one and see how it is calling itself. That's all about a program on depth first search. We will see the demonstration for this one. In this video, we will develop functions for graph traversals, that is breadth first search and depth first search. I have an example graph. I will show that graph. See, this is a graph, a simple graph I have taken with 6 vertices and few edges only. We'll be performing breadth first search and depth first search on this graph. And I have already prepared a adjacency matrix for this graph. This is the adjacency matrix. Though I have only 6 vertices, I have taken a matrix of size 4 by 4 because there is no vertex with index 0. See, I'm using this portion of I'm using only this portion of two-dimensional array. I'm not using 0th row and 0th column. So you can observe that 0th row and 0th column, they all have value zeros. So as when I did board work, I have started using vertices from 1 onward. So that is the reason I am skipping this vertex 0. Total 6 vertices, I have taken a matrix of order 7 by 7. Then for performing breadth first search, I require a queue data structure. So I have already taken a header file for queue, and this queue is using linked list. Already I have the functions like enqueue, dequeue as well as isEmpty functions. These are useful in performing breadth first search. Now let us write a function for breadth first search. Void breadth first search. It should take a matrix, that is G. First dimensions are not required. Second dimensions I have to pass, that is 7. And what is the starting point and what are the dimensions of a matrix, that is 7 by 7. Now inside this, what all the variables I require, I will be declaring them whenever I use. So first of all, I need a variable that is for start of a traversal. Then I need a queue, so I will say struct queue, I will declare a queue. And here on the top, I should include queue.h, that is the header file. Then here I need an array, that is visited array, of size 7, and this should be initialized with a 0, means none of the vertices so far visited. Then the first thing I should do is I should visit the starting vertex. So I will print that starting vertex. I have taken it in I. Then also I should mark visited of I as 1 to show that this already visited. And I should enqueue I. So I is enqueued. Now I should perform a repeating task by picking one vertex at a time and exploring it. So for that, while loop, while not is empty queue. So I don't have to pass a parameter queue. This is a I don't have to pass parameter q because there's a queue using linked list. Now each time I will take out a vertex from a queue. So say dq, I'll get a vertex and I should start exploring it. So for exploration, I will take one more variable, that is j, that should start from 1, and as long as j is less than 7, that less than n and j plus plus, n is the dimensions. Then every time I should check if there is an edge and vertex is visited or not. So if g of I comma j is equals to 1 means there is an edge, and visited of j is still 0 means it is not yet visited, then I will print that to show that it is visited. So I should print j and I should mark visited of j as 1 because it's already visited now, and also I should enqueue j, and here I should declare one more variable, that is j. So this is a breadth first search function. Now upon this graph, let us call breadth first search from main function. Here I will call breadth first search, and I should pass g as a parameter, that is graph two-dimensional array, and the starting vertex I will give it as 1. Then the number of vertices are 7, that is dimensions are 7 actually. Number of vertices are 6, but dimensions are 7. Let us run this. Oh, there is an error. So where I have gone wrong? Okay. Struct queue is incompatible type. Let us check. Oh, yes. We are using a queue using linked list, so we don't have to declare or create anything. This is not a queue using array. Directly, this queue class is having front and rear pointer already declared, because for implementing a queue using linked list, we need just front and rear pointers. So I can directly start using the queue in the program. So I don't have to declare anything. So it's already there. So let us run it now. Yes, it is successful. Let us see the result. See, for breadth first search, I got the result as 1, 2, 3, 4, 5, 6. I will change the starting vertex. Starting vertex was 1, so I will say starting vertex is 4. Let us see what happens now. So for 4, 2, 3, 5, 6, then afterwards 1. How we got this result? Let us look at the graph. See, in the graph, when we are starting from 4, and 4 is explored means the adjacent vertices are 2 and 3 and 4, 5 and 6. Yes. So 4, 2, 3, 5, 6. Then afterwards we can reach 1. So yes, it is correct. Now if I give the starting vertex as 5, then I should get the answer like 4, then 2, 3, 6 and 1. First it should go on 4, then for 4, adjacent vertices are 2, 3, 6, then 1. So 5, 4, 2, 3, 6 and 1. Let us try with vertex 5. Yes, 5, 4, 2, 3, 6 and 1. Yes, perfect. If I give the starting vertex as 3, then for 3 it should be 1, 4, then 2, 5, 6. If I change it to 3, 1, 4, 2, sorry, 3, 1, 4, 2, 5, 6. Yes, perfect. So our breadth first search is working perfectly. Now let us write a function for depth first search. Depth first search is a recursive function. It should take a graph as parameter. So the first parameter is empty and the second one is 7. Then I should give the starting vertex and also the dimensions. Now inside this we require a visited array. So I will declare it as a static type so that it is accessible in every call. So this is static size, it's 7, and I will make it as 0. So this is static array. Then every time we check that, if that starting vertex is visited or not. If visited of starting vertex is equals to 0, means it is not yet visited, then we will check if there is an, then we will print that one, print that vertex that saying that it is visited. So I am giving the name as start only. Then we have to start exploring this vertex. So for that we will take a variable j. J starts from 1 onwards and j is less than n and j plus plus. And every time we check that if there is an edge from I, that is starting vertex, to j, if this is equal to 1, and also check that if it is not visited of j is still equal to 0, then we call depth first search recursively by passing array, and j will be the starting vertex and the number of vertices are n, that is the dimensions of a matrix are n. That's all. So it's a very simple program for depth first search because it is recursive. Let us call depth first search. Instead of breadth first search, we will call depth first search and we will call it upon first vertex. Starting vertex is 1. Oops, I did not declare a variable j, so I will declare a variable j. So I got an error. You can see that. See, I am showing you the errors so that if you type and you face any errors, you learn how to remove the errors. Yes, it is successful. Oh, it is printing so many values. So it has gone into infinite calling. So let us see what is the problem, where we have gone wrong. So it's not stopping at all. One thing we did is, after printing this one, after visiting a vertex, we should mark it as visited. We have not marked them as visited. That is the reason they are being explored again and again. Should be made as 1. So this part I missed it. So now it is marked as 1. So it will not be explored once again. So let us run it now. Yes, the result is 1, 2, 4, 3, 5, 6. How we got this result? Let us check it. Starting vertex was 1. 1, 2, 4. Then from 4, 3 and 5 and 6 are adjacent. So first 3, then 5, then 6. We are visiting, see, remember, we are exploring them in the same order, that is numerical order. So first 3 is visited, then 5, then 6, because 3 comes first, so 3 is smaller. So in the numerical order, they are being visited, though we can visit them in any order. So we can visit them in random order, first 5, then 3, then 6. So we can change the order, but we have to change the code. Now let us change the starting index. The starting index, let us make it as 4. So for 4, it will be 2, then 1, then 3, then 5, 6. 4, 2, 1, 3, 5, 6. If I give the starting index as 4, let us see what happens. Yes, 4, 2, 1, 3, 5, 6. It's perfect. So that's all. You can try this program and you can take your own graph and take some values. You can try it for directed graphs also. So draw the graph first and prepare a matrix, then write these functions and try them. This topic is about spanning trees. So in this video, I'll explain you what does it mean by spanning tree and what does it mean by minimum cost spanning tree. Then further, we have the topics like Prim's algorithm for finding minimum cost spanning tree and Kruskal's algorithm for finding minimum cost spanning tree. We will study this in next videos. So in this video, let us understand what is spanning tree. Spanning tree is a subgraph of a graph having all vertices of a graph. Like here I have 4 vertices, all 4 vertices, but n minus 1 edges, means the number of vertices minus 1 edges, so that there is no cycle formed by those edges and graph must be connected. So I'll define it formally. Like this is a graph, G is VE, G is equals to VE, and this is the number of vertices, we call it as N, and this is the number of edges, we call it as E. Now what is the spanning tree? Spanning tree, if I say S is the spanning tree, then it is a subgraph of a graph. We can find a spanning tree only if graph is connected. Then this spanning tree should have set of vertices and edges where number of vertices are same as number of this vertices and the number of edges should be equal to number of vertices minus 1. Number of vertices, total vertices minus 1. And there should not be any cycle. So this was all formal definitions. Now let us understand it in simple terms. So for this graph, I will show you what does it mean by spanning tree. This graph is having 4 vertices. So I must take all 4 vertices. Okay, 4 vertices are taken. Then, as there are 4 vertices, I should take only 3 edges. 1, 2, 3. Total there are 6 edges. I have taken only 3. This is a spanning tree. I'll take one more example. 1, 2, 3 and 4. I'll connect them like this. These 3 edges I have taken. Is it also a spanning tree? Yes. This is a spanning tree for this graph, and even this is also a spanning tree. So it means more than one spanning trees are possible. Yes, more than one spanning trees are possible. I will draw one more. 4 vertices I have taken. 3 edges. Yes, 1, 2, 3. Yes. Is it a spanning tree? No, it is having a cycle. It's not a spanning tree. And you can see that there is a vertex 3 which is not connected. So it should be connected and it should not have any cycle. Then we say it's a spanning tree. This is not a spanning tree. Then I'll draw a few more. See, these are also spanning trees. So various spanning trees are possible for a given graph. Can we calculate how many spanning trees are possible for a graph? Let us see. See how many vertices are there? 4 vertices. Then how many edges are there? 6 edges. Then for 4 vertices, how many edges must be there? Just 3 edges must be there. Means 4 minus 1. So from the set of edges, that is set of edges, I should select 4 minus 1 edges. So C V minus 1. That is 4 minus 1. So in how many ways I can select? That many spanning trees are possible. So out of 6 vertices, 3 vertices can be selected in how many ways? So 6 C 3 ways. So for this example graph, it is 6 C 3 ways. Yes, with this I can get the answer. But let us see something. If I take like this, without labels I am showing here, this is also 3 edges, but this is forming a cycle. This is also edges, but it's forming a cycle. 2 cycles from this one. If I take this 1, 2 and 3. So this is 1, 2 and 3. This is 1, 2 and 4. Then if I take this, this will also form a cycle. Yes. And even this will form a cycle. So 1, 2, 3, 4, 4 cycles are possible. I should not take those set of edges which are forming cycles. So total 4 I could find out, right? And there are 4 cycles in this one. And those cycles are formed by 3 edges, not more than 3 edges, because we are selecting maximum 3 edges. Whatever the number of edges we are selecting, we should see that a cycle is formed using those many edges or less number of edges also. So find out all those cycles, not more than 3 edges, and subtract that one. So minus cycles. So minus 4. 20 minus 4. So this gives 16 spanning trees. So yes, for this graph, 16 spanning trees are possible. So once again I repeat, how many edges we have, then how many edges we have to select. So they can be selected in 6C3 ways for as per our example. Minus how many cycles are formed by using 3 or less edges. So out of 3 edges we found there are 3 cycles possible. So that 4 I have subtracted and I got 16 different spanning trees. So if I generate all, I can generate 16 different spanning trees. I have taken only 4 here, right? This was not a spanning tree. Now next thing I will explain you what does it mean by minimum cost spanning tree. So for explaining minimum cost spanning tree, I have given weights to the edges of a graph. The weight for edge from 1 to 2 is 2 and 2 to 4 is 1. So I have given the weights. Now let us understand the problem. We want a spanning tree like these such that the cost of total spanning tree must be minimum. So cost means the total weights of all the edges that are included in that spanning tree. So already I have few spanning trees. Let us give those weights to this and check what is the cost. See, this edge cost is 2 and this is 5 and this is 3. So total cost is 10 for this spanning tree. And for this one, this is 5, this is 6 and 3. So this is 14. And for this, it is 5 and this edge is 4 and this edge is 6. So this is 15. Total cost is 15. So we are getting different cost, you can see. So till here, this looks like smallest. Then this one, 2 and this is 1. This edge is 1 and this is 3. So this is 6. Oh, this is more smaller. So I did not try all 16 spanning trees, just I have taken 4 and out of these 4 I got a minimum cost spanning tree as this one. So maybe this is the minimum cost or 12 more are possible. So I should try out all of them and select the best one, right? So that's the problem. We want a minimum cost spanning tree. So there are some algorithms like Prim's algorithm and Kruskal's algorithm for finding minimum cost spanning tree that we will learn in next videos. So that's all in this video. In this video, we will see Prim's algorithm for finding minimum cost spanning tree. So in the previous video already we have learned about spanning tree and the minimum cost spanning tree. So now let us see what does Prim has suggested for finding a minimum cost spanning tree. So for explanation, I have taken a weighted non-directed graph and it is connected graph. All the vertices are connected. So yes, we can find a spanning tree or minimum cost spanning tree. Now let us learn the procedure given by Prim's. So Prim's algorithm. Let us learn it step by step. So the very first step, Prim says that select a minimum cost edge from the graph. The minimum cost out of all these edges is 1, 6, 1 to 6. So first select that one. So this is selected. Now follow the steps very carefully. Next step is repeating step. So always we will be performing same thing. So let us see what is that repeating step. Now from the graph, select a minimum cost edge, next minimum cost edge, but it must be connected to already selected vertices. Selected vertices are 1 and 6. So it should be connected to those selected vertices. So if I look into the graph, the minimum one is this one. And next is this one, next is this one. No, don't say take those edges. Select the one which is connected. So for one, connected one is this one, which is of 25. And for sixth, connected one is this one, that is 18. So select this one, 18, that is 6 to 5. So next edge is 6 to 5, 18. Now repeat the same thing. Select the minimum but connected. So from 1 it is 25, from 5, 16, 12 and 11. So 12 is minimum. So select 12. Now next, from 1, 6, 5 and 4, find out the minimum connected. This is 25, this is 16. For this one, this is 11 and this is 10. So 10 is minimum. Take that minimum. This is 3 to 4 or 4 to 3, which is of weight 10. Now the selected vertices are 1, 6, 5, 4, 3. We have to select the minimum one which is connected to any one of these. So from 1 it is 25, this is 16 and this is 11, and from here 9 is there. So okay, select that as minimum. So 2 and it is 9, weight is 9. Then the next minimum is 2 to 7, that is connected to 2. Connected to 2. 6. Yes. So what is the total cost? 5 plus 18 plus 12 plus 10, 9 and 6, 60. So the total cost is 60. So this is a minimum cost spanning tree suggested by Prims. We have followed the algorithm and we got the minimum cost spanning tree. Now the question is why he said that it must be connected. See, we have to achieve two things. First is it must be a spanning tree. So tree will be connected and it will not have cycles. Yes. Second thing is we want minimum. So the first preference is it should be connected so that it's a tree. So if I look at the steps that I have performed, so first I selected this, then this one. Up to here, if you see, it's a tree only, connected only. The next connected. So if you stop in between also, if you perform few steps and stop, if you don't complete, still you get a tree only. So that is the reason Prim has suggested focus on tree, try to maintain it as a tree, right? Then check for minimum edge. So this is the how Prim's algorithm works. Now let us do some analysis on Prim's algorithm. How much time it is taking? See, what is the work we are doing here? We are generating n-1 edges and forming a spanning tree. We are scanning through and selecting n-1 edges. So this is definitely v-1. This is v-1, n-1. So n-1 edges we are selecting. And every time we are checking the connected one and finding minimum out of the connected edges. So how much time it will take for finding the minimum edge? So let us say maximum we are checking all edges and from there we are selecting minimum connected edges. So the number of edges are E. So the time taken by Prim's algorithm is V into E. V is number of vertices and E is number of edges. This is also linear, this is also linear. So we can say this is n into n, that is n square. So we can say this one n into n square. So the time taken by Prim's algorithm is n square. Then if you are using some heap data structure for finding minimum edge from the set of edges, then the time can be reduced to number of vertices minus 1 into log e edges. So if you see this is linear n and this is logarithmic, so we can say log n. So the time complexity of Prim's algorithm will be n log n if a faster method is used for finding a minimum cost edge. Like we can use a heap or red black tree for finding minimum edge. Then one more thing about Prim's algorithm. See, if I have a graph which is not a connected graph, if it is not a connected graph, this is a non-connected graph. If I run Prim's algorithm on this one, then it will start from this minimum cost edge and it will try to select the next connected and next connected, so it will never reach on the second component because it is not connected. Yes, we already know that for a non-connected graph we cannot find a spanning tree at all. But what happens if I run Prim's algorithm on this one? So Prim's algorithm may find out a minimum cost spanning tree for one of the component. One of the component it can find out. Because they are not connected, it will never reach on the second component. So that's all. This is the analysis of Prim's algorithm. Next we will look at a program on Prim's algorithm for finding minimum cost spanning tree. In the previous video we have already seen Prim's algorithm. I have just shown you the working. Now for the same working we have to write a program. So based on the working, how to convert it into a program, let us learn about it. And one more thing, remember, for converting any algorithm into a program, you need to identify two things. First is, what is the data structure you require? Unless you know the data structure, unless you represent it in the form of data structures, you cannot solve it. The next thing is the instructions. Instructions, whatever the procedure is, that same thing you have to write in any language. So the basic thing is data structure. Most of the time students miss this. They will try to directly go on the instructions, but unless you know the clear idea of data structure, you should not go on instructions. So this is important. So this video should give you an approach for converting any algorithm into a program. So for writing a program, we need to have two things. We have to understand what should be the data structure used for the program and what should be the operations. So operation we have already seen in the previous video. That was just board work or paperwork we have seen. Now same thing we have to write it in the form of C language instructions. First of all, let us look at data structure that we require. So for that I have taken an example here. This is a graph. In the previous video I have used the same graph, just the values are different here. Now, how to represent this graph? On pen and paper you can do it like this, but inside the C program or in any program, how do you represent this? So a graph is represented as a two-dimensional array like a matrix. So this is a two-dimensional array, that is adjacency matrix for this graph. If you observe, as it is non-directed graph, I have taken the edges 1 to 6 as well as 6 to 1. Both I have taken and its value is 5. So if you observe here, 1 to 6 it is 5 as well as 6 to 1 also it is 5. So likewise I have filled all those values. This is ready. So we need a two-dimensional array, that is adjacency matrix, that is having the cost of the edges. So let us call that matrix as a cost adjacency matrix. And one more thing up to observe here is I have vertices 1, 2, 3, 4, 5, 6, 7. So I have the vertices starting from 1 ending at 7, but arrays in C, C++ or in any language, they start from 0 onwards. So I want from 1 only. So I have taken the size of this is 8 by 8. So 0 to 7 and 0 to 7. This 0th row and 0th column, I am not using it. And one last thing to observe. Wherever there is no edge, I have marked it with a hyphen, that is dashes. I have marked the hyphen there. That means infinity. That means infinity. If you are filling an array in a program, then put some maximum value there. If this is integer type array, then put their maximum integer value. Alright, so those dashes are maximum integer value. I cannot fill them, it looks very congested. So to make it easily readable, I have just written the values. Now next thing that we need is, whatever the spanning tree that we are getting, we have to select the edges and we have to store that spanning tree. So for that I have taken a two-dimensional array with 2 rows and 6 columns, and I am calling it as T. So here I will be storing spanning tree. So if you remember, in the previous video we saw that in Prim's algorithm we first select the minimum cost edge, that is 1, 6. So here I will be writing 1, 6. Here I will be writing 1, 6. Next edge, if you remember, we have taken this 6, 5. So I will be writing 6, 5 here, 5, 6, whatever it comes here. So in this way, I will fill up this with edges. So edges will have 2 vertices. So for that, I have taken 2 rows. And in a spanning tree, we will have 6 edges. So I have taken the size as 6. Next, we have one more data structure, that is an array called near. What is the use? I will show you. Now, next thing, I will first demonstrate the working of Prim's algorithm within these data structures. I will use these data structures. I will fill them by following the procedures we learned in the previous video. Then I will write it as a C program. So first let us see how we can use these data structures and work. Let us run Prim's algorithm. See, Prim says that first of all you find out the minimum cost edge, select that edge. So which is the minimum cost edge out of all these? 5, and it is 1, 6. First step, that is initial step of Prim's. Select that one, 1, 6. I will select 1, 6. So where I should store that 1, 6? Here. But before that, how do you find the minimum one? Where do you check and find out the minimum one? This is on paper. For the same thing, this is there in the memory, in the data structure. So from this you have to find out minimum. So you can check all that matrix, entire matrix, and find out the minimum. So if you check all these values, the minimum value is 5. And it is here also. So but if you observe, this is having duplicated values. 5 is 2 times, 25 is 2 times. So do you have to check the entire matrix? No. If you check only the lower triangular or the upper triangular, that will be sufficient. So you can check any portion. So check any part of it, either lower triangular part or upper triangular part, and find out the minimum. So if you look at this one from the middle, if I take a diagonal, upper diagonal part, this is upper triangular part, from this minimum is 1, 6. This is better, 1, 6. So find out the minimum one, that is initial step. So for this you can write on the code. You can write 2 for loops for finding the minimum from upper triangular part, that is 1, 6, and write down that 1, 6 here. 1 and 6. So this is the first initial edge that we are going to select, that is of minimum cost. Now next thing what Prim says that you have to select any other edge or vertex that is
connected and minimum. Connected and minimum. If you take minimum, the next minimum is 8. But we don't take this one in prims. We select the one which is connected. Means it should be connected to the selected one. So what we have selected so far, 1 and 6. So it should be connected to 1 or it should be connected to 6. So I should select the minimum one. So who is connected to 6? 5. Who is connected to 1? Only 2. So out of this we have to select minimum, right? So now we need to know who is connected and who is minimum. So for that I have taken this near array. I will explain about this one. See, initially near array is having all infinity. First of all, you should fill this with infinity. I did not kept it ready. Now I am showing you this should be infinity. And the size of the array I have taken as 8, that 0 to 7, because I need 1 to 7 only, because I have 7 vertices. Now as I have selected 1, 6, mark this as 1, 0 and 6 also as 0, because we have already included them. This 0 shows that this is there in the solution now, because we are getting a solution here, spanning tree here. Then what is the use of this near array? What we will do now is, after taking this 1, 6, what we should do now is find out all other vertices, whether they are near to 1 or near to 6. This is initial only, right? We are in the still initial part. Check whether they are nearer to 1 or nearer to 6. Take 1. Oh, this is 0. This we don't have to take. So take 2. Next one. 2. Is it nearer to 1 or nearer to 6? Nearer to whom? See, near to 1, the cost is 25. Nearer to 6, the cost is infinity. There is no edge. So if you check here, 2 to 1, 25. 2 to 6, infinity. So which is minimum? 25 is minimum. So 2 is nearer to 1. So in near array, mark it as 1. This is what we do. This means that vertex 2 is nearer to 1. Then next, vertex 3. So where to check? Here only. 3 to 1, infinity. 3 to 6, infinity. They are equal only. Both are infinity, infinity. So you can write any one. So I will take the second one. That is 6, because we are checking 1 and 6. So here I write 6. Then 4. 4 to 1, 4 to 6. Both are infinity. So write 6. Then 5 to 1, 5 to 6. This is 20. So this is infinity. This is 20. 5 is nearer to 6. So write 6 here. Then 7. 7 to 1, 7 to 6. Both are infinity. So write 6 here. So this shows that rest of the vertices are either nearer to 1 or nearer to 6. This is what we have to do it initially. Now the repeating steps will start. Till now we were doing initial work. So if we look at it quickly, first of all, first step what I did is, from this I found the minimum and I have taken that edge here, 1, 6. Then I have updated this near array and I found the rest of the vertices are nearer to 1 or nearer to 6. Now the repeating steps. Now what I am doing now, whatever I am starting now, will be going on repeating. Same thing I'll be doing again and again. So observe this. Now first step in this one is, from this find out minimum. What minimum? 2 to 1, 3 to 6, 4 to 6, 5 to 6, 7 to 6. 2 to 1, 3 to 6, 4 to 6, 5 to 6, 7 to 6. Which is minimum? Because we have to take another vertex that is connected to these only, 1 and 6 only. So this and this, we have only 2 connected, that is 25 and 5. 5 to 6 or 6 to 5, that is 20. So where to find out this one? See, this one, index, right? Index 2, 1. So here check 2, 1, 25. 3, 6, 3, 6, infinity. 4, 6, 4, infinity. 5, 6, 5, 20. 6 is 20. Then 6, 6, leave it. 7, because this is already 0. 7, 6, 7, 6 is infinity. Out of this, which is minimum? 20 is minimum. So that edge we should include. So mark here 5, 6, 5, 6, 5, 6. This is the next edge that we are going to include. See, this is the first one we have included, right? This is the first one, then this is the second one. Now next thing is, we have to update this array. How to update? First of all, mark 5, location 5 as 0. What does it mean by 0? We have included it. Don't check it again. We have included it. Now, how many vertices we have? 1, 6, 5. Rest of the vertices have the nearest vertex. 2 is nearer to 1, 3 is nearer to 6, 4 is nearer to 6, 7 is nearer to 6. Now we have to check, is it nearer to 5 than that existing vertex? So let us check. 2 to 5, 2 to 5, infinity. So 1 is better. 3 to 5, and right now it is 3 to 6. Which is smaller? 3 to 6 and 3 to 5. If you compare this, both are equal. So as I am writing the second value, so let us write down that 3 to 5 is infinity and 3 to 6 is also infinity. Both are same. So let it be 6 only. See, remember, we are right now looking at this 5. We are comparing with this one. Suppose let us call it as k. K is 5. So we are checking whether the other vertices are nearer to 5 or not. Now next thing, 4. Let us look at 4. 4 to 5. 4 to 5. 4 to 5 is 16. And 4 to 6. 4 to 6 is infinity. See, this near table is showing that 4 is nearer to 6, that is infinity. But now 4 to 5 is 16, which is smaller, 5. So update it to 5. Then these two are 0, 0, leave them. Seventh one. 7 is nearer to 6. This near table says that 7 is nearer to 6. The reason, it was compared with 1 and 6, so it was nearer to 6. It is infinity. But now is it nearer to 5? 5. Check here. 7 to 5, 18. 7 to 6, infinity. So this is nearer to 5. That's it. So this is the complete one step. Complete one step. Now the step is repeating. One more time. Second step. What was the thing we have done in the step? First find out minimum. Which minimum? Which is minimum h. 2, 1, 3, 6, 4, 5, 7, 5, leaving these zeros. 2, 1, how much? 2, 1 is 25. And 3, 6, 3, 6 is infinity. 4, 5 is 16. And 7, 5 is 18. So which is smaller? This one is smaller. This one, 4, 5 is 16. So mark here 4, 5. This is one thing. The next thing, we have to update this one. Right now we selected vertex 4. Now check all other vertices whether they are nearer to 4. But before that, make this as 0. So we should not check this 1 and 4 and 5 and 6 because they are already included. So rest of the vertices I should update. 2 to 1, 25. 2 to 4 is infinity. Check here. 2 to 1 is 25. 2 to 4 is infinity. So 1 is better. It is nearer to 1. Then 3 to 6 and 3 to 4. So 3 to 6 is infinity. 3 to 4 is 8. Oh, this is nearer. So update this one. Then 4, 5, 6, you leave them. 7. 7 to 5 and 7 to 4. 7 to 5 is 18. 7 to 4 is 14. So it's nearer to 4. Second step completed. Now I will do it quickly. Find out the minimum one. 2, 1 is 25 and 3, 4 is 8 and 7, 4 is 14. So 8 is smaller. Select this one. So that is 3, 4. Mark here 3, 4 and this is 3 and make this as 0. Then check rest of the vertices. Who are there? 2 and 7. Are they nearer to 3 or that same thing is correct? So 2 to 1. 2 to 1, 25. Then 2 to 3. 2 to 3 is 12. Oh, this is nearer to 3. Mark it as 3. Then 7 to 4 and 7 to 3. 7 to 4 is 14 and 7 to 3 is infinity. So it's nearer to 4 only. That's better. Step is completed. The next, find the minimum out of this. 2 to 3, 7 to 4. 2 to 3 is 12 and 7 to 4 is 14. So 12 is smaller. So 2 to 3 is selected. So this is 2 to 3. Right? And the k value is now what? 2. We selected this and make it as 0. And update. Only one thing I have to update. 7 to 4 or 7 to 2. 7 to 4 is how much? 14 and 7 to 2. Oh, I missed this one. 7 to 2 or 2 to 7 is 10. I did not mark this. So 7 to 2 is 10. So this should be 10. And 2 to 7 is also 10. So 7 to 2. So 7 to 2 is 10 and 7 to 4 is 18. Which is smaller? This one is smaller. Modify this one. Step is completed. Now again the step is repeating. Find out minimum. Only this is minimum. What is that? 2 to 7. 2 to 7 is included. Update and mark this as 0. Update this. Nothing will be updated because all of them are zeros. Your procedure ends because we have finished selecting all 6 edges. So what are edges? 1 to 6, this one, then 5 to 6, this one, then 4 to 5, this one, then 3 to 4, this edge, then 2 to 3, this edge, then 2 to 7, this edge. If you look at the spanning tree, we got it like this: 1 to 6, then 6 to 5, and 5 to 4, that is 4 to 5, then 3 to 4, then 2 to 3, then 2 to 7. And this is 5 and 20 and 16, 8 and 12 and 10. This is the minimum cost spanning tree. This tree is showing about this one. So I have drawn the diagram for this one. So that's all about the working of the Prim's algorithm. Now I will write on the pieces of code that is required. I cannot write on the complete program here. It needs a lot of space. So I'll be showing it in pieces. Then after this, you will have a video showing you the demonstration of this one. I will write on the program and show you. You can see the code, and also PDF will be available. You can download that PDF. So let us write on the pieces of code for doing all these things, that is Prim's algorithm. So here I have taken data structures. This is a cost adjacency matrix. So I am declaring them as a global variable. So there is no main function. It has not yet started. So this is outside main function. So main may start from here. Let us say void main or int main, whatever it is. Okay. So here is the main function. Before the main function I have defined. Let me show you what are the things I have written. Hash define I 32767. This is the maximum integer in 16-bit integer, and this is I, infinity, right? We need infinity. I said that at many places we are using infinity. Then I have a cost adjacency matrix of size 8 by 8 because there are 7 vertices and this is 8 by 8, right? So I have initialized all those values. So initialization I have done directly. This is the first row, everything is infinity here, and the second row infinity, infinity 25, and 3 infinity is 5 and infinity. Infinity, infinity 25, 3 infinity is 5 and infinity. As it is, I have initialized this. So I have not written everything. So now you can see that this is the whole thing I have to write down here. So that matrix is prepared here. Now the next thing that we require is near array, and if you remember initially this was infinity, all were infinity. This is the first one, is still marked as infinity. So I have taken an array of size 8 called near, and this is initialized with infinity. The next thing that I need is a 2-dimensional array with 2 rows and 6 columns for storing spanning tree, that is solution of this problem. So that array I have taken here, 2, 6. So all these 3 data structures are global for the main function. Now the main function starts. So I'll just remove few things from here and I will write on the main function. So here I have written initial steps. See, in Prim's algorithm there were initial steps. So what we did, we have found out the minimum cost edge first, from where this upper triangular part, right? Upper triangular part. And we have included that edge here. And we mark that edge as 0 here, right? For 1 and 6 we mark that as 0. And then we updated near array. All those steps I have done here. Let us see. See, these were the declaration and hash defined that I have kept it in small size. Main function is starting from here. These are the variables that I may be using in my algorithm. So I have declared them I, j, k, u, v, n, and minimum is, I have to find out the minimum, right? So for that I need a variable min. So I am assigning it to infinity, initial value. Then these follow. Finding the minimum cost edge, minimum value. From where? Cost, right? That is cost adjacency matrix. So for accessing that matrix, I need 2 for loops. 2 for loops are there, I and j. And for every cost of I, j, I am checking is it minimum, less than minimum. If so, I am changing the new minimum. I am changing it to new minimum. And I am also recording that u and v as I and j as u and v. So which is the edge that has given me minimum, I am finding out that one. So this is the simple thing, finding the minimum. Alright, so observe this one. And one more thing, I have started from 1, stopped at 10. So covering all rows. But every column I don't have to take, right? So I have to start the column that is beyond this diagonal. I should start from the diagonal, I should say. So I should start from this portion. I should not start from the beginning. So columns, I am starting from I onwards. J start from I to M. So this will take only upper triangular part. This is finding minimum cost edge. So where we will get the minimum cost edge? We get a minimum cost edge in U and V. Now that minimum cost edge, if you remember, we got 1, 6. So I wrote 1 here and 6 here. In T of 0, 0, 0, 0 and T of 1, 0. So T of 0, 0, U, T of 1, 0, V. I fill this. The next thing, I made this 1 and 6 as zeros here. 1 and 6 as 0 to show that these are already included. Near of U and near of V. This is U and this is V now, right? So that is made as 0. These are made as 0. The next thing, I have updated all these vertices. They are nearer to whom? 1 or 6, U or V. So here U is 1 and V is 6. We have checked. So where to check this one? Inside this cost adjacency matrix and find out they are nearer to 1 or nearer to 6. So this near array I have updated. So if you remember, I wrote like this. I got the value here 1 and this was 6 and this was 6 and this was also 6 and this was also 6, I think. This was 1 and the rest of them were 6. That was the initial work what we have done. Same thing. For I assign 1 to n, so I am checking all, right? Cost of u comma I is less than cost of I comma u and I comma v. That I is nearer to u or nearer to v. If it is smaller, that is nearer to u, then update it as u, otherwise v. So it's nearer to 1 or 6, whichever is nearer, write on that. And inside this, I should have one more condition. I missed that. I will write on that. I should take only those whose near is not equal to 0. Near of I is not equal to 0. Means it should not include this 1 and 6 and this one. Two conditions. So this should also be there. I should find out only for those which are not 0. So leaving the 0, I should do this. This will initialize. So initial step, find out whether they are nearer to 1 or nearer to 6. This is initialize. Near array is initialize. So this entire thing is initial work. Now next is the repetition work. Every time we select the minimum vertex from here and mark it as 0 and write down an edge here, then update near. So that is the code I have to write down. So I'll remove everything. Now I will write down the repeating procedure for this one. Here is the remaining part of the Prim's algorithm, the repeating steps. See, one edge already we have got it in the initial step, this one. And because there are 7 vertices, we need 6 edges for forming minimum cost spanning tree. So one is already over, remaining are 5. There are n vertices, that is n is 7. We need 6. Out of that, 1 is already taken. So 7 minus 1 we have to do, that is 6. So here is a loop, the outermost loop, this is the loop for finding out remaining edges up to n minus 1. 0th one already we have taken, so we have to start from 1 onwards. So this is starting from 1 onwards. So remaining edges. So from here to here. This is the complete task, the repeating steps. Now in repeating steps, what we were doing, finding the minimum of this. Minimum of what? 2, 1, 3, 6, 4, 6, 5, 6, 7, 6. Out of all these edges, whichever is smaller, that we were finding out. So for finding minimum, here is a loop. First of all, minimum is assigned, a variable minimum is assigned with infinity. Then for loop starts from 1 to n, from 1 to n. So this loop is taking variable j. So j is starting from index 1 onwards. This is starting from index 1 onwards. Now it will take only those which are not 0. So this is the condition, not 0. And it has to find minimum. So with this minimum variable, we'll compare every time. If the cost is less than minimum, we will change the minimum. And also we will record that which is giving us minimum value, k. So I'll trace this and show you there. See, j is 1. This is near of j. And near of j is 0. Don't take it. Then this is j is 2. And this is near of j. So 2, 1. We have to find out the cost of j and near of j. Cost of j and near of j. So this is the meaning, j comma near of j, that is j and near of j. Then it will be finding out the minimum of all these. So wherever is minimum, we will make k point there. So we know already that 5 comma 6 is smaller, so k will be pointing here. So for the first step, repeating step, we will get k as 5. K as 5. So this is the minimum. Now likewise in every step it will be finding out minimum. So we have already seen the procedure, so I will not be tracing it again, just showing you the meaning of the code here. Once that k is found, what we were doing, you remember, we were writing this 5 and 6 here. 5 in this place, that is k, and a near of k here. T of 0 at this place we were writing k, and here near of k. T of 0 comma I k, T of 1 comma I near of k. Then we were making this as 0, that is near of k as 0, near of k as 0. Then we were checking about other vertices whether they are nearer to k, and we were updating this near array. So this is updation of near array. As this loop is finished, again I am using j here. J and near of j, cost of j comma near of j, and cost of j comma k, whichever is smaller, it will update that. If it is smaller, it will update k, otherwise it will leave it as it is. This updation of near array. So these are the steps that we were doing. We were finding the minimum one. This is the code for finding minimum, and we were setting this here and updating near array, updating near array. And at the end of the for loop, we will have the result. So just print this one. So I don't have space here, so I wrote print t, means we have to print this two-dimensional array. All the edges we have to print. So that's all. This is the code and this is the working of Prim's algorithm. Once you finish this, I suggest you watch this video once again and try to do these things by yourself. If you do it once by yourself, then you can solve any new problem by yourself. And the main important thing is data structure, deciding the data structure. You can take different data structures also, and you can change the logic also a little bit, but the procedure will be same, right? The way it is done may be different. Okay, like here I have taken it as a 2 row and 6 columns. You can make it as 6 rows and 2 columns. Here I am using near array, so I am just writing nearest edge vertex. I am writing. You can write on the edge also. So you can take a different approach. So decide what data structure you require. So I suggest you practice it once by yourself using pen and paper. This portion. This is nothing. This is nothing. If you are able to do this, you can write on the logic. Loops, you know, variable declarations, you know, everything is simple only. So that's all in this video. In the next video, we'll find the demonstration of this code. I will write on the code and run it. Now you know everything, just I have to run the code and show you, and the PDF will also be available along with it. Let us write a program for Prim's algorithm. Already I have started a project. This is a C++ project I have taken. Here I have a hash defined for maximum integer. So you remember I have shown you that I is a constant, that is symbolic constant. I will use it as infinity. And this is a cost matrix, cost adjacency matrix of size 8 by 8. So 8 rows and 8 columns are there, where I am not using 0th row and 0th column. And the actual cost adjacency matrix is starting from 1 comma 1 onwards, right? From here onwards it's starting. So I am skipping zeros, that is 0th row and 0th column. Now next is near array, that we have already seen on whiteboard, that it will find out the vertices are near to which connected vertex, means the vertices which are already in solution. So and the size is 8. Again here 0th one I will not be using, I will be using from 1 to 7. Then this is for the solution, that is tree is for spanning tree, generating a spanning tree, 2 rows and 7 columns, that 6 will also be sufficient. I'll make it 6. Now here is a main function. In this I will write on Prim's algorithm. So first of all I will declare some variables that are required, that is I, j, k, 3 variables, and u and v are the vertices that I need, and also n, that is number of vertices. We have 7 vertices, and min, that is for finding the minimum every time. So I will take the value infinity. To find smaller value we need to have a larger value with us, so I is infinity. Now if any more variable required, I will come back here and declare them. Now let us start. The very first thing in the initial step of Prim's algorithm is to find the minimum cost edge from all these. So as I said, I will be taking the upper triangular part only and then find out the minimum one from there. So for that, I will take two for loops for I assign 1 onwards, right? I is less than equal to n and I plus plus. This will scan through rows and this j will scan through column, but it should start from I onwards so that it can access only the upper triangular part. Then j plus plus. Then every time we will find out whether cost of an edge I comma j, if it is less than min, then we will change this min to cost of that edge I comma j, and also we will set u as I and v as j. So here we got an edge, right? The minimum cost edge we got. So with these two for loops, we'll be getting the minimum cost edge in the form of u comma v. So that has to be stored in a solution, that is spanning tree. T of 0 comma 0 assign u and T of 1 first row and 0th column assign v. So we got this one. And also we have an array called that is near, and we have to update that array near, right? And before that, in the near array at location that is u as well as v, I should set them as 0 because already we have included them in the solution. So these have to be declared as 0. I've made them, initialize them as 0. Now I have to update or initialize, I should say, near array. So for that I will use for loop for I assign 1 onwards and I is less than equal to n and I plus plus. And in this one I have to check all other vertices whether they are nearer to u or nearer to v, right? Remember we are doing the initial work. So if the cost of an edge from I to u, if this is less than cost of an edge from I to v, if this is small, first one is small, then we will set near of I as u. Otherwise we will set near of I as v, near of I as v. So even if they are equal also, it will set as v, right? If u is less, then it will take u, otherwise it will set it as v. I'll remove these brackets. Now this is initialization of near array. Now we are ready. Now we have to include the rest of the edges. For this the procedure is repeating. So for that I will take a for loop, and for I starts from 1 onwards because at the 0th location we already have an edge in the solution. So for that we have this I, and I should be less than n minus 1 edges will be taking. So this is I plus plus. Now we have to get remaining set of edges, that is n minus 1 edges. So 1 is already done. So remaining edges we have to take. So for this one, first of all, we'll find out from the near array which one is minimum. So we have to scan through this near array. So for that I will take a loop starting with the j assign 1 onwards because we are using near array from 1 onwards. So less than equal to n and j plus plus. So what we have to do here is we have to find out which one is minimum. So remember, before writing the condition I should have minimum already having a infinity value, that is largest value with it. So set minimum to initialize minimum to I, then check here if cost of j comma near of j, right? You remember this code I have already explained you on whiteboard. I'm just typing the code and running the program to give you a demo. And that is less than min. If so, if at all, then we will set k assign j, and also we will change min to cost of that j comma near of j. These two things will do. So with this we'll get the k for which we have the minimum value. And one more thing, inside the condition we have to include only those whose near of j is not equal to 0, right? So this condition is also there. We should not come back to the same edge every time. The vertices which are already included, we should not consider them. So this is the condition, and checking the minimum one and finding the minimum one. So whichever is minimum, that will be set in k. Now, once we are out of this for loop, that is J for loop, we got the answer, that is minimum one. So T of 0th row and ith column assign, we got an edge. So what is that edge? It's K, right? And T of first row then ith column is assigned with near of K, near of K. So we got an edge. And once this is done, we have to modify near of K and set it as 0. Means this vertex is already included. We are not going to use it again. Now we have to modify the near array. See, the first step is to find out the minimum one, that is nearest one, and select it, keep it into the solution. Then now update near array to check whether other vertices are nearer to K or not. So for that, again I have to run a for loop. So this for loop, again I will use J here. J assign 1 onwards, and J is less than or equal to N and J plus plus. And what we do here every time is check if, first of all, near of that J should not be equal to 0. Means the vertices which are already included, we should not consider them. And find out whether cost of J comma K is less than cost of J comma near of J. If so, then modify near of J as K. Means this vertex is nearer to K. That's it. We should modify all these things. So once this is modified, then again the procedure will repeat. So this is the repetition for rest of the edges, and this is the code what we have seen on whiteboard. Now the remaining part is printing the solution. Now let us print the solution. So for this for loop, I can use I now because I am outside that outer loop. For I assign 0, I is less than n minus 1 edges, we will be having I plus plus, and just we have to print. So C out, I will print the values. First one is T of 0 of I, and second one is, I will put the brackets here. I will put them inside the bracket. Okay, so this will put an opening bracket, then comma, this is the next thing, then after this second one. So as an edge I am showing it as an order pair, so T of 1 comma I. Then let us close the bracket. This is the closing bracket. The next is NL. That's all. So let us compile and see if there are any mistake. If there are any errors, I will remove the errors. Yeah, K is not initialized and used. Anyway, now let us run the program and see if there are anything left. If any mistakes, I will remove those errors. First, let us run the program. Yeah, this is the output. It is displaying 1 6, then again 1 6. Actually it should be 5 6, right? 5 6, then 4 5. Yeah, 5 6 is coming here, 4 5 is also coming here, then 3 4 is okay, then we have 7 2 2 2 3 also. So there is something missed here. Let us look at it. Condition, yeah, here I am checking the conditions. Near of J is not equal to 0. Yes, here also. Oh, here I have missed the condition. I have to write the condition here also. While initializing the array, I should say near of I is not equal to 0, then only check U or V. This is the first initialization of near array. So here I missed it, so I have written that condition now. So we know well that near of array should not be equal to 0. If it's 0 means we have already included the vertex, we don't have to include it again. Let us run it and check once again. Yes, this is the prims result that we have seen on the whiteboard, that is 1 to 6 and 5 to 6, then 4 to 5, then 3 to 4, then 2 to 3, then 7 to 2. Yes, this is perfect. So that's all. This is the prims algorithm. So you can type this program by yourself on your PC and you can test it. And it's easy. You can easily rewrite the code once you have done practice on it. And there is a PDF available after along with this video. Check for the resource. You will find a folder on the right hand side panel. So just click on it. You can find the PDF and you can download the PDF. So that's all. Try this program by yourself.
In this video, we look at Kruskal's method for finding minimum cost spanning tree. This is the simplest and easy method. Already we have seen Prim's method. This is more simpler than Prim's method. Let us use Kruskal's method and find the minimum cost spanning tree for this graph. So let us start. See, there is no initial step here. All the steps are repeating only. So what is that repeating step? Always select a minimum cost edge. That's it. So what is the minimum cost edge in this graph? The smallest edge in this graph is 1 to 6. So let us take that edge 1 to 6 and its cost is 5. Then select the next minimum. Next minimum is 2 to 7. This is 2 to 7 and the cost is 8. The next minimum is 9, that is 2 to 3. So 2 to 3. This is 9. Next minimum is 10, that is 3 to 4. Select 3 to 4 and this is 10. The next minimum is 4 to 7. Select that one. No, this is forming a cycle. Yes, Kruskal says that always select a minimum cost edge, but make sure that they are not forming a cycle. If it is forming a cycle, just skip that one. Okay, don't take this one. This is forming a cycle. The next minimum is 4 to 5, that is 12. This is 12. Next minimum is 16, this one, that is 5 to 7. If I take, it will form a cycle. It will be a closed circuit, right? So don't take that one. The next minimum is what? 18. Okay, 5 to 6, select it. So this is 18. That's all. There are total 7 vertices and I have selected 6 edges. And the cost of this tree is 16. So already we have got the similar tree in Prim's algorithm also. So the same cost, it is 60. So once again I repeat the procedure. Kruskal says that always select a minimum cost edge from the graph and make sure that selection of that vertex is not forming a cycle. If it is forming a cycle, then go to the next minimum edge. That's all about Kruskal's method. Now let us do some analysis. What is the time taken by this algorithm? See, the time taken depends on the number of edges it has selected. So it is selecting number of vertices minus 1 edges, these many edges, v minus 1, that is 7 minus 1, 6 edges, 1, 2, 3, 4, 5, 6, yes. Then while selecting each edge, it is finding out the minimum cost edge from all the edges. So the time taken for finding a minimum from all set of edges is E. So the total time is V into E. This is N and this is E. This is linear, this is also linear. So we can write it as N into N. So the time is order of N square. Kruskal's method is order of N square time. Independent of the data structure it is using, whether it is using adjacency matrix or adjacency list, we are not bothered about that. We are just talking about the work done here using pen and paper. So it's order of N square. Then, can we improve this Kruskal's method? Yes, we can improve. See, always finding a minimum cost edge. So there is a data structure called heap, which always gives you minimum value or maximum value. So min heap always gives minimum value. So we can take the benefit of min heap for always picking up a minimum cost edge. So finding a minimum value from heap takes log n time. So this is log n. This is log n. Log e actually. So instead of log e, I can write n. So n into log n. So the time complexity of Kruskal method is n log n if heap is used. Then next, comparison between Kruskal and Prim's. So in the Prim's algorithm, the focus is more on finding a tree rather than minimum tree. But here, more focus is on finding a minimum tree than forming a tree itself. If it is violating tree, Kruskal says don't take that edge. So main focus is on minimum. So this is the difference between the approach of these two algorithms. Let us see if a graph is non-connected graph, how Kruskal works. I'll take a non-connected graph. Yeah, here I have taken a non-connected graph. There are two components in a graph. If I run Kruskal's algorithm, then what it will do? It will always select minimum cost edge. So it will select this one, then this one, then this one. This is forming a cycle, so it will not take this one. 4, then 5, it will select this one. 6, it will select this one. 7 is forming a cycle, it will not select this one. So there are total 7 vertices. It should actually select 6 edges. But how many it has selected? 1, 2, 3, 4, 5 only it has selected. 1 is missing. But because they were forming cycles, it has not included them. So if you see the result, what do you find? If there are more than one components in a graph, it will find a spanning tree for each component individually, but not for the entire graph. Because if the graph is not connected, you cannot find spanning tree for the graph. But it is possible to find the spanning trees for components of a graph. So Kruskal can find spanning trees for individual components. This was not possible in Prim's algorithm. So that's all. So we'll look at a demonstration program on Kruskal's algorithm. So that's all in this video.
The topic is disjoint subsets. This is useful for detecting cycles in the graph. So this is useful in Kruskal's algorithm. That is the reason I am covering the topic before Kruskal's algorithm. Let us understand what does it mean by disjoint subset. See, if you have a universal set, that is 1, 2, 3, 4, 5, 6 to 10. I have taken an example, a universal set, collection of 10 elements are there. Now if I take that subset, I have two subsets here, A and B. Just look at the things what I am showing, okay? A and B. If you check the numbers here, 3, 5, 9, 4, 7, 8, 10. If you take the intersection of these two, intersection is 5. So if you have subsets A, and if you take intersection with subset B, then the result is 5. So disjoint subset means if you take the intersection, the result is, there is no common element among them. Now, we use this for detecting cycles, so we need some data structure for representing. So how it is represented? We will see the data structure, that is the memory or array, as well as diagrammatic representation. So two things we have to focus on. So let us see. This is a universal set of 10 elements. I assume that every element is a set in itself. Itself is a set. So for each, there is a node drawn here. 10 nodes are there. And how to show that itself is a set? Negative value shows it's a set. So we use this notation that negative number shows that it's a set or head of a set. For every number in an array, you find it's -1, right? So ignore 0 because I'm not using 0. We have the starting number 1 onward. So ignore this one. So all these are -1. It shows that each element is a set in itself. Like who is the head or parent of 1? Itself. 2, itself. 3, itself, and so on. Now let us come to the next thing. Now from here you can understand, right? Exact meaning you can get from here. Now I have set A and set B. Look at set A, 3, 5, 9. So this means that these three elements together are forming a set. So in this we have to select one of the element as a parent or head of that set. So we'll select one of the element. Out of this I have selected 3 as a head. And 5 and 9 are pointing on that one to show that that is parent, or it means we belong to a set where 3 is also present. That is the meaning. So 3, 5, 9, they belong to same set. Now here everything was -1. How we represent here? So I'll show it here. I have an empty array here, that same array. Now I have to show this set A. So for showing that 5 and 9 are shown as children of 3. So at 5 I will write 3. And for 9 also I will write it as 3. Then at 3 I have to write some negative value to show that this is a head or a parent of a set. So I will write -3. Minus is negative. Okay, what is this 3? This 3 means total elements in this one. Yes, there are 3 elements. Next, if you look at this set, 4, 7, 8, 9, there are total 4 elements, and I have selected 4 as a head, right? That number is 4, and the 7, 8 and 10 are pointing on to 4. So 4 is a parent or head. And 7, 9, 10 says that we belong to set 4. We belong to set 4. So 7, 8 and 10. Here I will write down 4, 4, 4. And at 4, I have to write some negative number like -1. So just writing -1 is not much useful. So we write the total number of nodes in this one. Now here total number of nodes are also 4. So I will write 4 here. This 4 doesn't mean this 4, right? This 4 means number of nodes. So total number of nodes are 4. So here 4 is written. This is how we represent sets in an array. So from that universal set, we have prepared one subset A, one subset B. So these elements are like 3, 3, 3. These are forming a subset that is A, and this 4 and the 7 and 8 and 10 are forming a set that is B. These are forming a set. What about the rest of the elements? They are not yet included. So let us put all of them as -1. These are -1. So that's all. This is the representation of disjoint subsets in a universal set. On this we perform two operations that are union and find. Union operation and find operation. Let us look at these operations, and union is also called as weighted union and find is called as collapsing find. So I'll explain what does it mean. I'll remove this and show you. Let us say I want to perform A union B. Perform A union B. This is mathematical operation. Now if we perform union, the set of elements will be 3, 4, 5, 7, 8, 9 and 10. These two are combined together and there is nothing common, so nothing is discarded. Now how do you show diagrammatically? Diagrammatically I have to make any one as a parent, right? Only one as a parent, not both. So which one? Shall I make 3 as a parent for all or 4 as a parent for all? Whoever is having more elements, you select that one as parent. That's what weighted union. That's weighted union. So this is having more elements. So let us put 4 there. And 4 is already having 7 and 8 and 10. Then what about this 3? Along with its children, 3 will be pointing on this one. 3 will point on this. So this is 5 and this is 9. So all these nodes are joined together. They are together, they are connected, right? Under 4. These were independent, two different sets. There was nothing common. Now they are joined together, they became a single set. Now let us see how it is done inside the array. Actually the operation we perform inside an array. This is the diagrammatic representation. So what we do is, who is the parent of this set A? 3, right? Who is the parent of this set B? 4. So this is 3 or 4. Which is a smaller negative number, right? Negative numbers. This is -4 is smaller. Means it is having more elements. Or if you take positive, who is greater? 4 is greater. So that is having more elements. So what we do is, the parent of this set will have 4 here. So this 3 says that my parent is 4. Then what about 5? 5 says that my parent is 3 and 3 says that my parent is 4. Now this was -3 and this is -4. Total it is -7. So we add all that together. This means that 4 is having total 7 nodes. Total 7 elements are there in that set 4. So if you watch here, 1, 2, 3, 4, 5, 6, 7 are there. Now if you check who is the parent of 4, 5, 5 parent is 3, 3's parent is 4. So the parent of 5 is 4, parent of 9 is 4, 10 is also 4, 8 is also 4, 7 is also 4. So this is how union is done. So I will write down a simple code for this one here for performing union. Union of head of a set, let us say U, and head of a set that is V. Let us say head of a set is 3 and this is 4. Let us say I am performing union on this, that is 3 and 4. So for performing this one, I should check whose value is smaller. Actually it is negative, so I should check for smaller. If S of U is less than S of V, then who will become parent? S of U will become parent. But in S of U, we will write down the total value, that is -3 -4 we added and wrote here, right? So that is S of U plus S of V, and then we will change S of V's parent as now U. So we'll make U as a parent if U is greater. Else S of V, we will add these two and write them S of U and V together, right? Then next is S of U will change to V. So that's what. See, this was having less number of elements, so 4 became parent. Otherwise, we can make it other way also. Like 3 will be parent and 4 comes under this, and under this we will have 7 and 8 and 10, right? And here we will have 2 that are 5 and 9. But we don't do like this, because who is having more element? 4 is having more element. Otherwise 3 will become parent if 3 is having more. So just how it looks like if 3 becomes parent, I have shown you. But this is correct, so this is wrong, right? We don't need this. Now back on this one. This is union operation. So as a C language function, we can implement this and we can say it is void union. It will perform union on this one. So one will be made as parent of another, and the total nodes are stored in the parent. This is union operation. Now, one important thing. How to know that there is a cycle? See, suppose the vertices, let us say 5 and 10. 5 belong to which set? Parent is 4. 10 belong to which set? Parent is 4. Oh, they already are in a single set. If you join them, it will form a cycle. If there is an edge from 5 to 10 and if you are joining, it will form a cycle. That's how it is useful. The purpose of making sets is, see, if you take in this case, find 5, 3, find 10, 4, they are in different sets. We can connect them, the edge 5 to 10. If they belong to same set, don't connect 5 and 10. It will form a cycle. That's it. This is so simple thing. To detect whether there is a cycle or not, this is used. So I have already explained you union. Now let us see find. What is this find? Find means we want to find out who is the parent of any node. Parent of 5. So 5's parent is 3, 3's parent is 4. So parent of 5 is 4. Parent of 9. 9 is 3, 3 is 4. Parent of 9 is 4. So find out the parent, that is topmost node, root node. So from here if you see, 9 says 3, 3 says 4, 4 says minus 7 means 4 is the parent. Minus, negative, so it's a parent. So this is find operation. Find 10. 10 says what? If you check 10 says 4, come to 4. This is negative, so 4 is a parent. So find operation means finding out who is a parent. Alright? So let us see this operation, how to find. For find I have written a function here, find u. It means find 9 suppose. So the result should be 4 to show that 9 belongs to a set whose leader or parent is 4. So how to check it in an array? Go to 9, take the value here, s of 9. Go to 9, take s of 9. And go to 3, take s of 3. Go to 4, take s of 4. And if it is negative, stop and take this one. Don't take the value, take this one. That's it. So we have to go on taking the value of s until we get a negative number, right? As long as we are getting a positive number, continue. So for that, I have already taken a variable x and I have assigned that u. Now with the help of x, I will do. So this can be done using while loop. While s of x is greater than 0, means positive. What to do? Inside x, assign the value s of x. That's it. Simple. So if you trace this now, if I say find 9, then x is 9, right? S of 9 is greater than 0? Yes, 3. Then x assign s of x. S of x is what? 3. So x becomes 3. Now next time x becomes 3. So s of 3, is it greater than 0? Yes, it is 4. Then s of 3 is what? 4. So this x becomes what? 4. Then s of 4, is it greater than 0? S of 4? No, it will stop. So what is the value of x now? It is 4. That's all. That's the result. So it means to find the parent of any element, just we have to follow the hierarchy and reach till the negative number in an array. This is simplest. So we got the parent now. Just return x. That's it. This is what find is. So we will find out the parent. Alright. This is a simple function. Now there is one more idea in this one, that is collapsing find. We will try to directly connect to the vertex to the parent directly. So you can find out, explore it by yourself. I have explained you the sufficient required things. that is union and find operation upon set, that are useful in our next algorithm, that is Kruskal's algorithm. So there I will not be explaining you union and find, I'll be using them. So that's all in this video. There is a demo also available on this one. In this video, we will look at a program for Kruskal's algorithm. In the previous video, we saw the working of Kruskal's algorithm. It's very simple. Always select a minimum cost edge. That's it. So it's very simplest one. We will write a program for this one. For writing a program, I have taken an example graph here. This is there already in Prim's algorithm. I have used the same graph. Now, for writing a program, two things are important: data structure and the operations. So first of all, decide the data structure. If your data structure is perfect and if you are able to work on it manually using pen and paper, then writing the program becomes damn easy. So I have a data structure here. Let us look at this. What are the data structures I have? See, I have taken array of edges. So if you remember in Prims, I have taken a adjacency matrix, that is cost matrix I have taken. But here I am not using adjacency matrix, but I am using list of edges. So let us see what are the contents. Already I have kept it filled. So this is an array of dimension 3 rows and 9 columns. Why 9? Because there are 9 edges. So if you look at the edges, first edge is 1 to 2, 1 to 2, and the cost is 25. 1 to 2, cost is 25, right? So first row is containing first vertex number, then second vertex number, and the last row, that is 2, index 2, is containing their cost. If you look at next 1 comma 6, next edge, from 1 there is an edge to 6, its value is 5, 1 6, its value is 5. Then let us take a vertex 2, 2 to 3 12, 2 to 7 10, 2 to 3 12, 2 to 7 10. Likewise, it is already filled. Then you already know the working of the algorithm. Always find the minimum edge. From this I have to select minimum. It's not a big task. Take out the minimum and include it in the solution. The next minimum include in the solution. But the edges that I have already included, I should not include them again, right? So for that, how to know whether it is included or not included? When we are selecting anyone, you should know that they are not included. So for that, I have an array of size 9, 0 to 8 to mark them included or not included. So from here, whichever edge I am selecting, I'll mark this as 1 there to show that this is included. If it is 0, it is not included. So this array will maintain the record of the edges so far included in the solution. Then for getting the solution also, I need a data structure. So that is, I will take a data structure here, that is T, which we have already used this in Prim's algorithm. So how many edges we will be getting? 6 edges. So 0, 1, 2, 3, 4, 5. So this is 0 to 6, 5, that is total 6 edges. So I'll be storing the result there in that data structure. Whenever you are picking up a minimum edge, you have to make sure that inclusion of that edge is not forming a cycle. How to detect a cycle? Yes, for detecting a cycle, we will use set operations that are union and find. So for that, I have an array called set, and I need, there are 7 vertices, right? 1 to 7. So 1 to 7 I have taken. So starting from 0, I am not using this one. So I put a cross mark there. I am not using it. I'll be using it from here. And all these are filled with -1 initially. Now how set and union, that is set operation union and find works, I will show you while tracing this one. So I will trace this Kruskal's algorithm, the procedure which we have already seen, by using this data structure, how they will work in this data structure. Then afterwards, I will write on a program. What all I am doing here, for that same thing, I will write a program. So let us see the tracing of Kruskal's algorithm upon this data structure, because we have this graph in this form now, in this form. This is on paper, this is inside memory. So let us see the working. For tracing Kruskal's algorithm, we already know that Kruskal doesn't have any initial steps. Everything is repeating step. And for knowing whether there is a cycle or not, we use sets, and already you have learned what is union and find, and weighted union and collapsing find, both we have seen. So let us follow the same thing here. We will use that one to check whether there is a cycle or not. Let us start the procedure. What is the procedure? Find out a minimum cost edge. Find out a minimum cost edge. So from this, we will trace this and find out minimum. So first minimum is 5. So let us call this as J. Let us call it as J, right? And here Is it included? No, it's not included. So now this is minimum. So find out whether it is forming a cycle or not. So for 1 and 6, check who is the parent. If their parent is same, they belong to same set, means they will form a cycle. This is the method. So let us check. Find 1 minus 1. Find 6 minus 6 minus 1. So they are parents of themselves, right? So if I draw it here, this is 1 and this is 6. So they are not forming a cycle. Their parents are different. One's parent is 1 and 6 parent is 6. They are not forming a cycle. So we can include this one. Let us include this in the solution. So let us put I here for filling this one. This is 1 and 6. And here at 1, because it is included, mark it as 1. This one we have included, mark it as 1. So this is over. Now perform union upon them. Weighted union on 1 comma 6. So as we have already learned weighted union, we will check. This is minus 1. That is also minus 1. Who is minimum? 1 is not smaller. So make 6 as a parent. So here I will write 6. And now there are total 2 vertices here. So this will be minus 2. So this comes under this one. 1 comes under this. And this will be pointing on this one. This is just like this. 1 says that my parent is 6. And 6 says that I am the parent of myself. I am the parent of his set. And I have 2 vertices, minus 2. That's all. Step is over. Now let us do it repeatedly. Let us do it repeatedly. Find the minimum. Next minimum. Who is the next minimum? Out of all these, this 8 is minimum. So this one. See, it is not included, right? 4 is not included. So that's how this is taken. And this is marked as 1. Now whether to include 3 and 4 or not. Find 3 and find 4. Find 3. 3 is a parent of itself. Find 4. 4 is a parent of itself. Right? These are 2 different. So there is no cycle. It will not form a cycle. Then 3 or 4, which is a smaller? Both are equal only. So we'll update this one and make that as parent. So we will write 4 here and this we will write as minus 2. This means that 3 says that my parent is 4, right? And 4 says that I am the leader of this set or head of this set, and there are 2 vertices in this set. That is 3 and 4. And this 3 and 4 are included here. 3 and 4 are included. So you perform union also, weighted union also, we have included this one. That's all. So same thing will repeat. Again, find out minimum. Which is minimum out of all these, which is not yet included. Don't include 1 and 4. Means don't take this 5 and 8. Other than this, this is next minimum. So this is J. 10 is J. Find 2 and 7. Find 2. Find 2 minus 1. Find 7 minus 1. So this means that this is 7 and this is 2. I will write like this. They are independent now. Then it means it's not forming a cycle. So you can include this one, 2 comma 7. 2 and 7 are included here. And this one, 3, is made as 1. It means it is included. Now we have to perform union. So 2 and 7 both are minus 1 minus 1. So this 2 will be pointing on 7. And here I will write 7. Now 7 says that there are 2 vertices under this set. 2. So we got 3 different sets now. Now again repeat. Same. Again the step is repeated. Find out minimum out of all these. Right? After 10 the next minimum is 12. This one. So this is J. Is it included? 2. Is it included? No, not included. Then find 2 and find 3 to find out whether they are forming a cycle. Find 2. 2. Who is the parent of 2? 7. Find 3. Who is the parent of 3? That is 4. So yes, they are different. So we can join them. It is not forming a cycle. So who is smaller? 4 or 7? Both are equal only. So what we do here is, at this place we will write 7. Now this says that there are total 4 vertices under this one. So this 4 comes under this. So I will draw it once again here. 4, and under that we have 3, and this is included here. So they are forming a single set. And at this 2, mark it as 1 to show that this is already included. And 2 comma 3, you write it here. This is included in the solution. 2 comma 3 is included. Now repeat the steps. Find out the minimum one. After 12, 14 is the next minimum. And find 4, find 7. Find 4, find 7. Find 4, parent is 7. Find 7, parent is 7. See, here if you check, find 4, 7. Find 7, 7. So both are same, 7, 7. Parent is same. 4 is under this 7 only. So this will form a cycle. Don't include this one. But this vertex, this edge, we cannot include it. That is sixth one. Mark it as 1. Next time, don't consider that one. It's not included in the solution, but this is over. This is finished. So just mark it as 1. So that's how we found a cycle, that there is a cycle when both their parents are same. For 4 also we got 7, for 7 also we got 7. Now next step, find out the next minimum, right? After 14, the next minimum is 16. This we get 4 comma 5. Whether 4 comma 5 can be included or not. Find 4. For find 4, 7, 7. 7 is the parent. In the diagram you can see. Find 5. 5 is not yet included. 5 is independent. 5 is independent, right? 5 is the parent of itself. So yes, this is not forming a cycle. So when it is not forming a cycle, include this 5. Make it as 1 here. Then this is 4 comma 5. 4 comma 5. Then we have to perform union. So 5 should go under this 7 because this is the parent of this one. And how many are there? Minus 4 and this is minus 1. So here we write 7 and now this is having minus 5. 5 vertices are there. 1, 2, 3, 4, 5. So now next, check the next one. Find the next minimum. This is over. After 16, the next minimum is 5 comma 7. This one. That is minimum. Find 5 and 5, 7. Find 5. Who is the parent? 7. Find 7. Who is the parent? 7 only because this is negative. So both are giving same. So this 5 and 7, they belong to single set. This will form a cycle. If they are belonging to same set, it is forming a cycle. So don't include this one. So don't include in the solution, but mark it as 1 to show that this is finished. Right? This is completed, included. This edge is gone, deleted now. Okay. Then next, find the next minimum. After 18, the next minimum is 20. 5 comma 6. 5 comma 6. Find 5, 7. Find 6, 6 itself is a parent. So find 5, 7, find 6, 6 only. These are different sets, so they are not forming a cycle. So just include this one. So this is 5 comma 6 included in the solution, 5 comma 6, and mark this as 1. This as 1. So seventh one is 1. This is included. Now that's all. See, actually we have finished all 6. We got all 6. That's all. We can stop here because we got n minus 1 edges and we got the solution. So this is the working. So in between the set is also there. So if you have already learned about sets or if you have not seen it, I suggest you go back and check it. This was there. Otherwise, it's very simple. Take minimum included, take minimum included. But forming a cycle or not, that's what we have to detect. And sets helped us. For sets, we will use collapsing, find and weighted union. So now I will write on the Kruskal's program, right? I will prepare this data structures and also I will write on the instruction. Let us look at a program. So already I have written piece of code for a program. Let us understand what is there. See, I have not yet started main function. I have just taken these data structures, this edge and set and include and t. So how I have declared, I will show you. See, this is maybe we want minimum, so we want some value that is infinity. For we have to find out minimum. So that's what I have written, the largest number there, I. This already I have shown you in Prim's algorithm. Now this is edges, a two-dimensional array, 3 rows and 9 columns. So first row contain first vertex and then second vertex and the cost of an edge. So this is forming one single edge, right? So I have taken it is row wise. So first row, first vertex number, second vertex number and the cost of edges. This is first data structure, this one. The next is sets. All are initialized with -1. For implementing sets, for checking cycle is formed or not. So initially, if you remember, this was -1, all were -1. All I have filled up with -1 and the size is 8. That is 0 to 7. So we will be using from 1 to 7. The first one we will not be using it. Then Whether to find whether this set should be considered or not considered, means deleted or not deleted, included or not included, we have an array that is included. If you remember, this was initialized with 0, then later on when I was including them, I was marking them as 1. So whether these edges are included or not, for that we need an array of size 9 because there are total 9 edges. And if you just write 0 here, everything will be initialized with 0. You don't have to put 0 9 times. Now next thing is a two-dimensional array with 2 rows and 6 columns for a solution that is spanning tree. I have this one. Now this is weighted union. Already we have discussed this one, right? So I will not explain this. This is a weighted union, and similarly collapsing find method also, function also we can write down. I have written just union. Find I don't have to show you, alright? Already there is a topic on this one. Now let us write down the main function for Kruskal's algorithm. The procedure is very simple. I will write on the code and I will explain you. Here I have written a main function for Kruskal's algorithm. Look at this one. See, these are the variables that I will be using. I for this preparing a tree solution, I was using here. That is starting with 0. And as we are including the edge, I will be increasing. Then j, k, n is number of vertices, e is the number of edges, minimum, for finding a minimum we need some variable, u and v for any edge, whichever edge, like 1, 6. So 1 is u and 6 is v. So for that I have declared the variables. Now if you look at the code, this is a simple loop, everything is repeating. So just a simple loop, this while loop. For I assigned is already 0, right? I is less than n minus 1 because we need n minus 1 edges. So this loop will repeat for n minus 1 times. That's it. And what it will do every time? Find out minimum edge. Out of all these edges, whichever value is minimum, and that value should not be included. Means it should not be 1, it should be 0. So that included should be 0 and that edge is minimum. If it is minimum, this for loop is finding out, this for loop is finding out minimum 1. If you got any minimum, change minimum, record it as k. See, suppose this is minimum, first one is minimum, we are taking it as k, mark it as k. While explaining I was saying j, okay, j I was using. Now here in the code I am using k here, mark it as k. J is used for scanning, but whichever is minimum, there k will be pointing. And also I am taking the edges u and v, whichever is minimum. Like suppose I have got the answer k as 1, then this is u, this is v, u and v, those two also I am taking. So this is portion, this for loop is for finding minimum. Just observe this one. What I have explained you, same thing is written here. So once you got u and v, check, find out that there when you perform find, they should not be same. Result of find means their parent should not be same. If parent is same, means it's forming a cycle. So if the find of u and v is not equal, means it's not forming a cycle, include this in the solution, u and v. So u and v inside t. This is t of 0, I and t of 1, I. Because I have used there, so at that place write on u, v. And perform union on u and v. That is, who are u and who are v here? This 1 and 6 are u and v. Perform union on this 1 and 6. So in this set. So whatever the find has given the result, upon them we have to perform union. Okay, not directly union of u, v. Find result, whatever the parent, whoever is parent, join their parents. So union of find of u and find of v. Then as we got an edge, increment I. Move to the next free space in this t. That's all. And also make this include of k, whichever edge we got, make that as 1. Mark it as 1. That edge as 1. Here we have to mark it as 1. Alright, whether it is included or not included, that was the minimum. We have finished with this edge, just mark it as 1. So this is outside if, not inside if, right? Whether include or not include. If it is forming a cycle, we will not include it. But we will not include in the solution, but we will mark it as 1 to show that this we are not going to consider again. That's all. This is repeating every time. And at the end, print the result. So this is the simplest algorithm. The coding is very simple. The main function is very small. I will code this and I will show you. I will write down the program code and show you. So you can watch the next video for demo. Let us look at the demo for Kruskal's algorithm for finding minimum cost spanning tree. For writing Kruskal's algorithm, already I have written few things here. See, the first thing is set of edges. This is already shown on whiteboard. Set of edges are there. 3 rows and 9 columns, because there are total 9 edges in our example graph, the graph which I have shown on whiteboard. If you have not seen that video, I suggest you go back and watch that video. Then this is the demonstration of that video. Here is first is the row of first vertex, then row of second vertex, then this is the row of cost of the edges. Total 9 edges are there. Then as we are using disjoint subset, so for that there is an array of size 8 here, because there are 7 vertices. So 0 to 7, that is 1 to 7 I'll be using. 0th one is not used. Then included, whether an edge is included in the solution or not. So for that we are maintaining an array, and that is all initialized to 0. Whenever we are including an edge, we are going to make it as 1. Then this is t of 2, 6 is an solution, that is spanning tree will be storing in this one, that is 2 rows and 6 columns, that is 0 to 5. Then for performing set operations, we have join, that is union, I should call it as union. And next is find, union and find operation. This we have already discussed, so I will call it as my union. Okay, my union, and that is u and v, it will perform union. This is a weighted union. And I was discussing about the collapsing find. This is the find, this is the code which I have shown on whiteboard, and this is the extra thing. I said that once you found the parent of any vertex, you can directly connect to it. So this is the code for connecting all those vertices directly to the parent that is coming along the path. So this is the extra code, and this is called as collapsing find. Now next, we have everything already. I have shown you these things, discussed these things. My union is there, and find and edges and set everything. Now let us write on the main function, that is the algorithm for Kruskal. Algorithm for Kruskal's algorithm is very simple. So what all the variables I require, I will declare them I, j, k, and u as well as v, and minimum for, and that let us initialize minimum to I, that is infinity. As a maximum integer, I am taking it as infinity, so it is initialized to I. And also the number of vertices are 7, and the number of edges, we have number of edges, that are 9 edges are there, so that is 9. E is 9. Now this comes inside one while loop, because there are no initialization part here. Everything is repeating step, so we have to write on entire thing in a loop. And for that I have to take total n-1 edges, so I is less than n-1 I will write on. So let us initialize I to 0 starting onwards. So I'll be getting n-1 edges, so inside this while loop we'll get all the edges. Now here we have to write on the logic. Now inside this outer loop, I have to find out a minimum cost edge. So for that I have to scan through the edges. So I will use j, and j starts from 0, j is less than e, that is number of edges, and j plus plus, this is j plus plus, and every time I have to find out a minimum cost edge. And the min I should initialize every time whenever I am selecting a minimum. So let us do it here. This is the right place for setting minimum value, that is minimum as infinity. Now inside this loop I will find out minimum if cost of an edge, so that is inside array, that is edges, and inside third row, so that is index 2, that is 0 is the first row, right, 1 is the second row, so 2 is the third row, and column is j, whatever the j value we are scanning. If that is less than minimum, then let us take u also, that is for first vertex we will take it for the edge first vertex, and second vertex in u and v. So that is edges of that is first edge is first vertex is in 0, so 0 of j, and then v is inside edges of 1 of j, whatever the minimum that we are getting. And also we should record this one, whichever j is giving minimum, let us record it in k, because once that edge is included, we are going to mark it as 1. Means once we have considered it, whether it is included in the solution or not, we are going to mark it as 1. Now once we are outside this for loop, we have a minimum cost edge. Now the question is whether we should include it in the solution or not. So for that we have to check whether it is forming a cycle or not. So for that we will call a find function, find, that is set function, find u, as well as we will find out v, both the values will find out. And these values should not be equal. If they are equal, means they already belong to same set, so by including this edge it will form a cycle. So if they are not equal, then we will include in the solution. So the solution is a T, that is spanning tree T of 0 of I assign U, and a T of 1 of I is assigned with V. As we have included this edge, then we should perform union on this one. So union, I have named it as my union. Okay, this is my union function, and in this I should find of U and find of V. I should join the parents, right? I should not join just the vertices, I should join their parents. So I have given find of U and find of V. This will perform union, and also we should move on to next I, because we have got one edge in the spanning tree. We got the result, right, inside the result. So one edge is included in the solution, so move to the next index for the next edge. Then at the end, outside this if, anyway, this edge we have already completed, so included should be made as, included of k should be made as 1, right? So here one more thing I missed here, whatever the edge you are taking, it should be included of that one should be equal to 0, right? Then only consider that one, otherwise don't take that edge. Means don't repeatedly take the same edges as minimum edge, otherwise it will always be finding the same edge as minimum edge. So if included is 0, then only take it, and once it is done, once you have found it as minimum, then at the end you make it as 1. So this is the entire while loop. So this is the simplest code of Kruskal's algorithm. That's all. We will get all minimum cost edges included in the solution. Now once it is done, we have a solution with us. So let us traverse through this solution array and display all the edges, that is all the edges that are included in the spanning tree. So we have n-1 edges, so I will print all of them. So I will use cout here, and I will display them as order pair, that is T of 0 comma I, and comma, next is comma, then T of 1 comma I, then close the bracket, then after that NL in a new line. That's all. So that's all with this algorithm for Kruskal. Let us run it, and if there are any errors, I will remove them. If any logical or syntax errors, let us remove them. Here I got the error because set is a array that is declared after the function call. So let us change this one. I am copying this one, cut from here. I should declare it before the function calls because the set array is not visible for them. So I have declared the array in the beginning. Let us run it now. Okay, are there any more errors? Yes, semicolon is missing. Let us see. Yeah, successful. Yeah, 1 6 3 4 2 7 and 2 3 4 5 5 6. This is what the result we have seen on whiteboard. So the same result we got, and you can see the order in which the edges are included. First is 1 6, then 3 4, that is the next minimum 8. This cost of this edge is 5, and the cost of this edge is 8, and I guess this is 10, and this is 12 something. Okay, and this is 16, and then this is 20. So this is how all the edges are included in the solution. So we got the result. So that's all in this video. You can try this program by yourself. If you do it by yourself once, don't try to just for an examination. If you are preparing, just don't mug it up. Do it by yourself, and if there are any variations possible, you can do that. You can take a data structure in different forms, right? I have taken these edges in the form of rows. You can take them in the form of columns, or you can use structures. There are many possibilities. Or in classes, you can make it as a class, edge as a class. So a lot of things you can do. So you can try this program and write the program by yourself. And there is a PDF available along with this video. So that's all in this video.